Now it's okay, right? So, fantastic. So, as I said, thank you for coming along. I hope you feel home in Seville. We are going to actually make a start with the program just to comply with the agenda. Just a minor last-minute change that unfortunately Professor Flavio Manenti from Politecnico di Milano is not here with us because he got COVID and he preferred not to travel last minute. That means that we can enjoy a longer talk from Roberto and Julia if they fancy, so please be my guest and, and expand your slides. And I was meant to read the health and safety protocol. This is I will pass it on to you guys later, but essentially we have emergency exits over there, and we have an assembly point outside the building. Just follow me, follow Jose, or the local people. We will guide you in case of an accident that we don't expect that to happen, really. Good, so I believe, Ana Belén, you want to say a few words as a project coordinator, or otherwise I will move on to the, right, so. Excellent. So without further ado, it is my pleasure to introduce our opening keynote today from Professor Roberto Rinaldi from Imperial College London, entitled Catalysis for Conversion of Lignin into Energy Carriers. Roberto, the floor is yours. Thank you very much.
Thank you very much, Thomas, for the kind introduction. Thank you very much, Jose, and all the organizing committee for inviting me to share some thoughts about catalysis for conversion of lignin into energy carriers. So, lignin is one of the three main polymers we have in nature. When you think about wood, for instance, this material here is made of wood. About 30% of this material is lignin, and the other 70% is basically cellulose and hemicellulose. Cellulose is a polymer that I know some of you may know. It's actually the same polymer we have in cotton. And hemicellulose is something more complicated, but it's also made of sugars, but from pentoses instead of glucose. So when we started the research in lignin in 2012, I was at the Max Planck Institute für Kohlenforschung in Mülheim an der Ruhr, Germany, and it was actually something very interesting because every talk I went that time, the major question was to burn or not to burn. And when we finish actually the talks about lignin, people always actually look at us like this. Okay, that lignin was actually to burn. But now, some years later, we can see here that things change. She grew up, and lignin is now something actually more interesting in the literature and research. And today I would like actually to present you something about how to burn this in the best way possible. That means how to transform lignin in liquid fuels, liquid transportation fuels. And at the end, if time allows, after 3 hours of my talk, then I will also actually talk about my thoughts on hydrodeoxygenation of lignin to value-added chemicals. But let's actually go here on cellulose. When we think about cellulose and we want to obtain, for instance, gasoline, let's actually just do this, this exercise here. We would actually then need actually a lot of deoxygenation and hydrogenation, in terms here hydrodeoxygenation, to bring the composition in terms of oxygen, carbon of cellulose and hemicelluloses close to zero in the case of gasoline, diesel, and kerosene. If we think about lignins, this distance is a little bit smaller, shorter, but still we need actually to remove some oxygen, and we still need actually to add some hydrogen. Well, this is a very simplified view of the problem, but serves to us to motivate us in a way that we can basically think about the hydrogen use. Because the hydrogen use is something very important when we are thinking about making fuels. Nowadays, hydrogen comes from natural gas. We are having serious problem in Europe. And, but in future, this will come from renewable sources. So in a world where hydrogen is there and as much as we can use, if we would actually do HGO of glucose from cellulose hydrolysis, this is the stoichiometry that we have. This is basically just a model reaction in which we transform glucose into an hexane, and if we find the catalyst for this reaction, we invest 7 molecules of hydrogen, we generate 6 molecules of water, and we incorporate 7 atoms of hydrogen here in the product fuel. So that means that we lost here 50% of the hydrogen as water. That is actually a very expensive way to produce water. I mean, tomorrow, Thomas will actually say the things in the other way around, how to use water to actually gain the hydrogen for the chemistries we do. This is the right way, but this is not really very much the right way. If we go to aromatics, we have a different thing, because now we are causing here the methoxylation of the lignin aromatics. We produce methanol that in principle could be utilized as a fuel. And here, as a model compound, we are producing propylbenzene. And we also release water. But if we actually do the balance of hydrogen in water and in the product fuel, we will arrive that here we just lost 26%. And if we actually decide to hydrogenate everything to cycloparaffins or cycloaliphatics. Well, if we do that, then the reduction in hydrogen loss is very, very much significant here, because then now we have, let me see here that I think it's better to use this. We have here then just 16% of hydrogen lost as water. This is not really because we are doing less hydrodeoxygenation. No, it's because we are now using the aromatic rings of lignin to basically store hydrogen, and for every ring we can actually store 3 moles of hydrogen. Well, does it make sense in terms of energy? Well, if we think about the storage of hydrogen, chemical energy, in aliphatic hydrocarbons, we would actually have as the simplest reaction possible the hydrogenation of benzene into cyclohexane. And this is, as most of hydrogenations, hydrogen transfer hydrogenations are different, but usually all hydrogenations and reduction processes, they are very exothermic. But when we actually do this storage, we see that we increase the enthalpy of combustion from 3,273 to up to 3,920 kilojoule per mole. And this is basically all the energy that you have from hydrogen is basically stored in this cyclohexane. So the full saturation of lignin aromatics in this way, in an approach that we have renewable hydrogen and we want to make chemical storage of this energy, this could also be something interesting, because what we have here is a molecule that can get a lot of hydrogens. And we are incorporating actually both atoms of hydrogen when we do the saturation of lignin. That means converting the phenolics into the cycloalkanes. And last but not least, here this chemical energy basically stays mostly in the product field. So this is actually something very interesting, and that's why we do still a lot of research in hydrotreatment of lignins. But once again, 10 years ago, we started actually to tackle this problem from another perspective, because lignin, different from cellulose, can be soluble in several normal solvents. For instance, alcohols, water in supercritical conditions, and all actually sorts of solvents. And when we started actually doing that, I mean, if we are thinking about hydrogenation with hydrogen, then this is an important study to do, because the solubility of hydrogen depends on the solvent, and this will probably very much define the mass transfer limitations we have when we go to a larger scale. But not only that, the solvent is also competing for the sites on the surface. So this can actually also tune the catalytic activity of the catalyst. So, and this was actually the very first review, I mean, from our work in lignin, that this manuscript is not suitable for angevin chemie because the phenyl ether is 2 words. Nowadays, we receive much longer review reports because we have a community now that is active. Not only actually some people that don't know the topic, and since it's very different from what they have done ever in their lives, they basically say, okay, let's find something easy to reject. And it was the way, but afterwards, this paper got 400 citations in this great journal. I mean, it's not really a problem. But I think she was a reviewer. So, but what is important here? And what is this very strange figure? Well, here we have 2-dimensional chromatography in which we separated the mixture here with a non-polar column and here with a short polar column in this direction, so that we can increase the resolution. And why is this important? Because when you do 1D, you may think that, oh, that peak there, here, yeah, this peak here for who is watching from YouTube, you think, oh, this is just one compound. But if you actually basically go here, you will see that all this line here, all these peaks here that we have, they are basically adding to form this peak. So the situation is much more complicated than we usually think. And the first results basically showed that we have too many minor components, and this basically makes the purification of the mixture for chemicals actually very expensive. So this would not really be so useful for chemicals. But for fuels, it might be, and I will show you a little bit later in this talk. But the conclusion we had here was burn it, yeah? Because, I mean, it's an interesting mixture of compounds, but unfortunately, the chemical industry does not really sell mixtures of compounds. And then in 2012, we also actually started working on hydrogen transfer reactions, in which we basically realized that with running nickel and 2-propanol, we could actually do this type of conversion here of phenolics derived from lignin under very mild conditions, and producing acetone here, and in addition, cyclohexanols. And several other transformations can actually be done by this very simple chemistry, or very simple catalytic system. Simple in practice, very complex basically in reality. And then we just thought why we should actually start from organosolv lignin, that 10 years ago people just thought that, okay, when we extract organosolv lignin, that means we cook wood or any lignocellulosic materials in a mixture of alcohol and water at 180 to 200 degrees C. Lignin basically detaches from the plant cell wall, and you have a liquor. And then when you remove the solvent, you have a dark brown powder that we call organosolved lignin. But there are much more things there than we can imagine apart from lignin. But then we just thought, okay, if we would start with the idea of the organosolve, but instead actually having here the catalyst and utilizing 2-propanol, both as hydrogen donor and the solvent to extract lignin, what would happen? And we did the experiment, and to our surprise, instead of obtaining a solid, we obtained the polymerized lignin oil. I mean, after a lot of characterization, we saw that instead of having a very complex mixture of products, it's still very complex, but we had very high yields of individual components. And not only that, we could actually separate the catalyst because runny nickel is magnetic and obtain a very good quality carbohydrate pulp and reutilize the catalyst because we utilize quite a lot of catalyst here. If you read the papers, you will see. But we can recycle the catalyst at least 7 times. After 7 times, Paola was a little bit tired. She said, no, it's working. So 7 times was enough for proving that the catalyst was recyclable. So this was the first time lignin was actually on the cover of Angewandte Chemie. And what was important from this experiment? What we provided to the literature as a difference? Well, it was not really only the fact that we could now obtain a mixture of monophenolics at high individual yields for each component, but also that we were demonstrating that lignin is not really that recalcitrant when it comes from the plant cell wall. And this is actually a misconception that we had in 2012, that lignin was something that nothing could break. Of course, nothing could break because it was already too degraded because of the pulping processes that form very stable carbon-carbon bonds. So thermodynamically, even that you have the catalyst, you cannot really change the fate of thermodynamics. You may actually change the freedom of the way, but not really the fate of thermodynamics. So, and by saying so, if we compare the activation energies for hydrolysis of these acetals here, that we call glycosylic bonds that occurs in cellulose, here hemicellulose, and here in lignin, we are showing here the beta-O4 linkage that is the most abundant in native lignin. What we see is that cellulose is protected by the packing of the crystalline structure, but both these structures here, if they are unprotected, you would see that the activation energy is quite close for acid hydrolysis. But when then you go actually for lignin, because of this OH group here, this is actually very labil, and it can be easily removed if you protonate, forming a carbocation, and this carbocation here then can start a number of other reactions leading to a very easy cleavage of this chemical bond. And you can see here that 3 kcal per mole, it's a very low number. You know, it's basically spontaneous to break if that thing is protonated. So, and if we do experimentally the things, and it's something new in our group, and we start to analyze basically the RCF and the chemical process history basically imprinted in the pulps, we will see that here cellulose and hemicellulose has a very high retention in the pulp, but lignin, since the very beginning, is already actually decreasing. We are already actually at temperatures as low as 140 degrees C, already doing some delignification. Of course, when we increase the temperature, we have further delignification, but hemicellulose is still actually a lot of hemicellulose there, and cellulose or glucans here the losses are much less because cellulose is really very well packed and protected physically against hydrolysis. And when we basically do an organosolve process, and we have then the acid solvolysis or hydrolysis of this beta-O4 linkage, what happens is that we will form a lot of intermediates that are very reactive, that are the Hebert ketones. And here we can also actually have this route here that forms these eno ethers that are very reactive as well. And these Hebert ketones, they are electrophiles. They have actually carbonyl groups, aldehydes, that can basically react at very harsh conditions of pulp with the aromatic rings via electrophilic aromatic substitution. These rings here are rich in electrons. This is poor. That means we can actually do condensation. And this basically makes the problems of technical lignins when we don't really control the reactivity of the system. But we recently just basically found another way that lignin is stabilized in RCF. This is in this preprint here. You can actually access the paper that was submitted. And, well, one reaction that happens when we have running nickel and lignin is the hydrodeoxygenation of this position, the benzylic position. This is a very, very easy reaction to take place. And when this happens, it's a very different situation from here, because here, if I do a protonation, I have water elimination forming this quite stable carbocation, benzylic carbocation. And this is an even more electrophilic species than a carbonyl. In this way, if there is actually a very rich, electron-rich compound here, we can actually have condensations forming structures that are different from those from nature. While here, since we actually replace this with a hydrogen, even in acidic conditions, this will not really get out of the structure forming this carbocation, so you don't really have condensation of lignin. So these in parts explain why we have some high yields, because we are protecting lignin by these selective processes, and on the same time we are also actually hydrogenating things that are formed by hydrolysis, the Hebert ketones. So there are two mechanisms there happening. We were able to quantify this via NMR, doing a very extensive fractionation. We found an easy way to do a fractionation of the lignin oil. And what we see when we compare the apparent molecular weight of these fractions and the amount of reduced beta-O4 in the total of beta-O4, reduced and non-reduced, and by reduced I mean the ones that contain this hydrogen here, is that the further the process goes in terms of the polymerization, more will be actually higher will be the population of reduced beta-O4 linkage. That means we are also actually doing the stabilization throughout basically the depolymerization process. Clearly, if you have a polymer interacting with a surface, this is a little bit more difficult to happen, but even here with 19,000 Daltons, you can see that we have 4% of the beta-O4 reduced. We cannot really say if it is actually at the ends or in the middle of the chain. NMR doesn't really allow us to do this right now, but this is what we found. And as I was telling you about the mixtures with very high yields of individual compounds, you can see that here the chromatogram, the 2D chromatogram, is much, much cleaner. Of course, we will also have the silane or hemicellulose alcohol products. You saw that decay also over time. But the polarity and the types of chemistry of these two classes of compounds allow them to be technically separated with ease. But we obtain here just as major compounds, just actually 3 or 4 peaks. Of course, if you go actually low in the threshold, you can actually see other things that are small intermediates that were not really reduced, or other intermediates. But in principle, what we see is that when we publish in Angevant, we put actually very low threshold to show everything, but this is in reality the chromatogram in 3D. And this was taken basically 20th of March 2013. Yeah, to prove that I am not really lying about the simplicity of these mixtures. And after that paper in Angevant, there were several other papers by several other great colleagues and friends. And by several ways, through different ways, people basically demonstrated that it's possible to obtain monophenolics at high yield if we have reductive conditions and a catalyst. And not only that, we can actually also tune the selectivity of which this propyl chain here is functionalized, yeah, with a double bond here, or a allylic alcohol, or an alcohol, or simply basically here just a propyl group. And also actually the size of this chain from C1, C2, and C3. In 2016, I mean, I was participating in a workshop like that, but actually from a project, a European project that was called Cascat Bell, led by David Serrano in Madrid. And we were actually there in the middle of the Czech Republic, and what we found is that on the way back, I was talking, me and Bert Verkhausen, we were seated together, and a bus trip that was supposed to take 35 minutes was a little bit longer, 2 hours, because we had a quite old bus, and the bus broke on the way. And then we basically had the time to basically start developing the ideas of this review paper that afterwards it became actually a landmark in this field, that basically shows that catalysis is not only dedicated for the very beginning or the very late stage that, okay, I have lignin, now let's do something out of this. No, to have the right lignins for the process, you need to use catalysis from the beginning of the process. Because if you don't really control the solvolysis processes and you don't really control the reactivity of the species, the lignin will actually get very complex. You still call lignin, but it's no longer lignin. It's a polymer derived from lignin, in which we see a lot of carbon-carbon bonds that are not native carbon-carbon bonds. But if we utilize catalysis in what we call catalytic upstream biorefining to make the extraction and have that mixture of phenolic compounds, then we could actually do the downstream to value. And this, all in all, is what we call lignin first biorefining. But this doesn't really mean lignin cellulose second, because by doing reductive processes on lignin, what happened is that the fragments that were detached, they will not reattach to the residual lignin in the pulp. So the pulps that are obtained by this process, they contain also much less lignin. Therefore, if you utilize these pulps for enzymatic catalysis, you obtain much higher yields of sugars. Yes, and now about catalysis and where we are, basically, we are more or less actually in 2020 when, I mean, the plague came and closed the labs and caused a lot of problems to all of us. And that time we were basically working, and we are still doing some works in this direction, of phosphidation of nickel to obtain nickel phosphide. And this is a liquid phase phosphidation, basically by cooking a nickel catalyst in 3-octyl phosphine. Everyone working in heterogeneous catalysis would say, okay, by doing so you will poison all the surface and you will not really have any activity because you are basically reacting this with phosphines and causing to block all the surface. But if you do this at 300 degrees C, 6 hours, the good thing is phosphines, they have very, very low vapor pressure. You can even actually do this in a closed glass flask. What you obtain is a mixture of phosphides. Here we varied a little bit of the stoichiometry. And what we saw is that we have formation of a nickel phosphide phase. However, when we start using the catalyst, I mean, this catalyst was getting better and better cycle by cycle when we were doing the hydrodeoxygenation of guaiacol. And what we could see is that the reason for that was that in the very first cycles here, we have the leaching of phosphines, and after 2 or 3 cycles, we have the stabilization here, and you can basically follow that losing a little bit of phosphines would not really destroy the catalytic activity. However, I call this phosphidides nickel catalyst because if you see here, the phase is no longer actually with any resemblance to the initial phase. I mean, the catalyst is stable, forms a phase that we don't know what it is. We did a lot of X-ray studies to understand these exhausts, shuns, and all the things, but we are still actually trying to understand what this is. And the real catalyst on the surface is nickel plus phosphidated nickel plus nickel phosphide. And this catalyst, when we apply to lignin oils, we can basically see that what we obtain is 2 classes or 3 classes of compounds. Here, a lower class of compounds that is close to gasoline, here kerosene and diesel, and here paraffins. And by controlling the pressure of hydrogen, you can direct the selectivity towards aromatics or to aliphatics. A good thing is that when we do this phosphidated nickel silica catalyst, what we obtain is very distinct cuts. And basically this reflects the C9 structures, the units of lignins, C18 with losses in hydrogen and the carbon in the side chain, and higher oligomers here. So if you would do actually distillation, this would be a much easier process to do distillation to obtain aviation fuels, gasoline, diesel, because here is what we do or we obtain when we are utilizing nickel on silica. That means we obtain a lot of compounds, but they are all beautifully here, and distillation of this can actually be a little bit more complicated if you want to have defined cuts. Well, and the important thing here was that the catalyst, even after 3 cycles and phenol and basically doing very forcing conditions, 300 degrees C, was still producing hydrocarbons, but okay, the catalyst starts deactivating, we still actually have some traces of phenols, but nickel silica, after the 3rd run, what happens here is that we have a lot of cyclohexanols, and the catalyst has totally different selectivity. Yeah? So by doing this approach, what happens is that we obtain distinct classes of aromatics and aliphatics that could basically serve as drop-in fuels. And this is something that the fuel industry always loves to hear, because it doesn't mean actually doesn't imply for them that they would need to change all the infrastructure they created over time. I mean, it's billions and trillions of capex, so drop-in solutions is good because of that. And we went further. We basically did here a stoichiometry experiment to see if we would actually, instead of utilizing cellulose and hemicellulose, the pulp, what we call holocellulose, to do gasification and steam reforming, we would obtain cellulosic hydrogen. This we could utilize to supply the hydrogen here. By shuffling this hydrogen from cellulose and hemicellulose to the lignin oil, we would be almost self-sufficient in hydrogen for the upgrading of this lignin oil to the fractions of diesel, biodiesel, kerosene, and other things. But if we go beyond burning, and I think I have 2 minutes more, yeah? So we also actually, together, the company Henkel, we showed something very interesting. That is, if we want actually to have laundry detergents, one of the main components is linear alkene benzene sulfonates, LAS. I mean, the market for these compounds is 14 billion. It will surpass this by 2031. And this molecule here, this part here, comes from petrochemistry. The sulfur also actually comes from petrochemistry because we need to do a lot of HGS to have our fuels without sulfur. The question is, do we need BTX out of lignin and then actually do the same thing, dropping, or could we actually utilize the phenols from lignin and then see if this works as surfactants? And the answer was yes, we can do this. This is the critical micellar concentration. The lower the better, because you just need a little of detergent to form micelles that will actually do the work of cleaning. And here what you see is the commercial one. And here you have basically with methyl guaiacol, with phenol, or guaiacol itself. And in all the cases here, you see that the critical micellar concentration is much lower. And if we go to more sophisticated products like these ones here, what we saw is that we can even actually have drops in the critical micellar concentration by a factor of 10. In principle, by utilizing this type of chemicals, we would be able to utilize 10 times less surfactant to do the same job. Well, this is a good thing, but if this is much better, why has the industry never actually done anything with guaiacol detergents? I mean, because we could actually obtain guaiacol from petroleum. It's not really complicated. The first step is the phenol production via benzene alkylation with propene, forming cumene, and then oxidation form phenol and acetone. Oxidation with hydrogen peroxide to form cathecol, then the methylation with the stearable methylating agent to guaiacol. We start with $1 per kilo and we end here to $10 to $20 per kilo for guaiacol. From wood, this is basically as a side product from the pulp, from that lignin oil. So if you put another methyl here, you multiply this by 3. And if you actually put 3 carbons there with the OH, we are already actually talking about fine chemicals. That would be 20,000 per kilo. And the price of LIS is $2 per kilo. So even that we would actually have this that's 10 times more expensive than benzene or phenol, we will still actually be with the products from lignin close to the LIS price we have in industry nowadays when we consider the performance that we would need 10 times less. So I hope that I could show you that the lignin first base approach, they can produce a lot of oxygenated phenols, guaiacols, syringols, that are very useful as protoform chemicals. And you could obtain BTX if you want. We also showed this. But this approach of BTX from lignin first oils is perhaps not really the best as a drop-in solution for petrochemistry, because the compounds we have already there, I mean, they are just waiting for us to use our chemical creativity to do something better than we have nowadays from protochemistry. And people, in most of the cases, want actually to defunctionalize everything, functionalizations that synthetically would be very expensive, and bring this to drop-in chemicals. But this is, to my opinion, is not really the best way. But drop-in energy-dense fuels, biofuels, can actually be something between these two worlds, in which we can obtain really very specific cuts of hydrocarbons for different types of applications as fuels. So with this, I would like actually to say thank you once again to the to the organizing committee for inviting me. Also actually say thank you to all the people here. Sergio is also here. He worked also in our group, and basically all the people who paid, and they give actually space, money, and all the things, and you for your attention. Thank you very much. If there are questions, I would be very happy to discuss them.
Thank you, Roberto. Very inspiring talk indeed, per usual with you. So thank you for this masterclass on indeed.
Thank you.
Right, so is there any question in the room or any comments to discuss with Roberto? Mel is first. She was faster than you, sorry.
Thank you for that nice talk. I have a question about the nickel phosphide catalyst. I guess, how does the nickel to phosphorus ratio, is it stable during the reaction as it's changing, or do you change the nickel to phosphorus ratio as you're running the reaction? Because I noticed there's quite a lot of changes. Is it just becoming less crystalline with a mixture of phases? Can you comment on that, please?
Yes, we can comment on this. We did actually high resolution TEM to see this, and also actually microanalysis basically of the spots, several spots of the catalyst, dimensions of 1 nanometer. And what we saw is that this distribution of phosphorus is not really very uniform. So there will be domains that are richer in phosphorus and domains that are basically not really that rich. So these are associated with different sites that are formed, and they cooperate in a way that we have this very nice outcome. Because so far, I've never seen a catalyst in batch condition that could be reutilized 3 times, utilizing something coming from lignin. So this is the reason why I highlighted this as something that is worth looking into, because there is something interesting there, but it's very difficult to comprehend basically the role of phosphorus and what is happening with this phosphorus in the reaction.
Whatever's happening, it seems to be working, so.
Yeah, it's working. I mean, for industry, this would be perfect because it works. But for publication, this is always complex because the colleagues, they are very purist, and they always want to know everything in a way that even they would not really know how to do. So that's that's the way. But it's not a problem. We like challenge, but there are questions that sometimes we cannot really answer with the technologies we have nowadays available. Yeah, I mean, operando would be great, but operando of very complex things, how could we do that? Mm-hmm. But it works. I mean, it's a good thing.
Roberto, thank you very much once again for an amazing presentation. It's more a comment, which I would like to hear from you,
Mm-hmm.
and it's more about scaling up of the technology that you have been working so hard for the last decade or so with amazing results. How do you see that? And the question is about your vision for scaling up of this technology, and how industry could be attracted by this new trend and these new findings that you have been published over the years, and they are so amazing. But there is still a gap between what is being done in the lab scale and industry. So what do you see that needs to change for that to come to reality?
Well, basically everything. Not only actually the way we consider the process, but the way we consider the products we obtain without actually the very strong tendency to always actually go for BTX, because this is what we have in the chemical industry, and unfortunately, either in chemistry or in chemical engineering, we do not really teach people to think more than that. So drop-in is a solution because we don't know actually how to do the things when they get more complicated. But the results show that we can obtain materials, performance materials, that are much better than anything coming from BTX. Then why we need actually to strip important functionality that, by the way, we don't even have the techniques to put it in synthetic organic chemistry. It would take 47 steps, was what actually artificial intelligence by IBM predicted for that ones that are with propyl and OH group there to be produced. So the point is, it needs to change everything. And it must actually start basically in academia, basically looking at other types of applications of these phenolics, starting basically from them. They are readily available in the literature, in Aldrich or other suppliers, and basically start thinking the problem through the point that let's consider that we have this guaiacol, this and this at this price. What products we would get? Because if the performance is 100 times better, I mean, then we can actually pay for this different chemistry, even that the product would be 50 times more expensive, because in the use, we would still actually be half less expensive. I hope that I could answer. In relation to RCF, we did actually some technical economic analysis, actually by we, I mean the National Renewable Laboratory led by Greg Beham in Colorado, and we participated in this study, and what we saw is that, of course, batch hydrogenations, they are very expensive because these reactions are very expensive. So the catalyst was even not really a problem, even considering palladium or rhodium, yeah? I mean, that means the capex to produce a reactor, to operate actually the volume you would like to have this commercial, it's very high. But you can actually go to flow reactors. You can actually do several other things. You can decouple the lignin extraction and the passivation. I mean, that same group actually showed very nice results because the condensation is not really that so fast that as people thought in the beginning. I mean, it takes place in a time frame of 1 to 3 hours. So there is still a lot to do. I mean, we are still actually perhaps in the very, very first 2 or 3 technology readiness levels, yeah? I mean, there are still actually a lot of things to do to understand better. But if we never do, we will never have the technologies that we need when oil will no longer be allowed to be used. This day will come, as for gas.
Thank you, Roberto. I think we have plenty of time to discuss with you over the coffee break.
Thank you.
Thank you very much again.
Thank you very much.
And we move on with the program. And the next speaker is coming from industry, from Green Delta, Germany. It's Julia Cilleruelo. Whenever you want, Julia. I will help you to upload the presentation if you want. Thank you, Robert. Actually, for the speakers having the presentation after the coffee break, you can just pass it on to me so we avoid some delays if you want. Okay. Yeah, if you want. I can just preload it. quitar el mío rápidamente. Poner el de Julia. Voy a quitar el mío. Vale, digamos que está bien. Toma, cárgale copia del escritorio y después ahora si quieres. Roberto, you need to talk to Melis later in the coffee break. We also started with a referee with a nickel phosphide catalyst for a different reaction. Yeah, the bloody ass things that were undoable to do, really. Characterize even the last electron, right? Melis and the FPS. So.
Where is the last electron of this phosphorus? The problem is that even we would find, they would not.
No, they will reject them. Sí, con el BIOALL workshop que viene ahí mismo. Porque aquí, madre mía, pero ya tiene video, transparencia. Copia la diversa y después la pasa.
Sorry for the small delay.
It's alright.
Okay, but we're starting now.
You have a pointer if you need it also?
Yes, it's here, no?
Yeah.
And then
Should be working, yeah, good.
And then I can pass the slides with these two buttons, I guess.
Yes.
Quite intuitive.
All right, so Julia, the floor is yours. Thank you very much.
Thank you for giving me the opportunity. My name is Julia, I work for Green Delta, and at Green Delta we do life cycle assessment. So today I'm gonna speak about what is life cycle assessment and also the OpenLCA project, which I really believe in and I think it's great. And if you are interested in life cycle assessment, I think you better hear about that. Maybe first I'd like to ask, did someone hear about life cycle assessment before? Put your hands up if you've heard about it. Good. And put your hands up if you've ever carried out a study in life cycle assessment or you've gone a bit further in life cycle assessment. Okay, good, thank you, because then I can assess who I'm talking with also. So in this presentation, I'll be speaking about life cycle assessment as an introduction, then OpenLCA as a tool for life cycle assessment, and also about Green Delta and who we are, and how we participate in this project. So to introduce life cycle assessment, I'd like to introduce maybe an idea first, which is very simple. Did anyone here buy a bamboo toothbrush in their lives? Okay. Good. People, I've asked this before in other presentations, and people are a bit shy. I don't know if people really say the truth, but you've heard about the bamboo toothbrush, okay? And so this is very simplified, let's say, example of what to do. Should I buy if I want to improve my environmental footprint and help the environment and sustainability, I have to maybe make choices in aspects of my everyday life, this personally. But then companies also have this type of decisions, and also governments in legislation, etc. But if we break it down to the simple example of should I be using a bamboo or a plastic toothbrush, then what's the answer? Because usually the bamboo toothbrush is well, it looks very appealing because it's made out of wood, but it also the marketing, etc., it's made so that we're really trapped in buying it because we think it's more sustainable. But life cycle assessment has the aim to really make a study to, through data, understand what is really the best choice environmentally speaking. And then that was a simple example, but a bit of a bigger example would be, for example, choosing an electric car versus a diesel car. And as I said, then this can extrapolate to legislation at a European level or at a huge company level, making one decision or the other. So through life cycle assessments, we can get more informed into how does my decision affect the environment. We'll see, because then we can also make a life cycle assessment for social issues and also economic. And then make a decision based on that. And so I was curious myself when I found the picture, what would be best, so bamboo or plastic toothbrush. And I found this study which compares plastic toothbrushes with bamboo toothbrushes with plastic reusable, so you can replace the, let's say, the head of the plastic toothbrush, and also electric toothbrush. And life cycle assessment covers a lot of impact categories. You've probably heard about carbon footprint, which is one result of life cycle assessment, but we can also understand the water footprint in a life cycle assessment, land use, acidification, human toxicity, eutrophication of water, ozone layer depletion. In the end, sustainability is not only speaking about carbon footprint, but it can really touch many aspects of the environment that can have different consequences. So it's important to understand more the big picture, and that's why we do life cycle assessment that tries to not only focus in carbon footprint. So climate change here, wrong button. Climate change here would be carbon footprint. If I speak like this, is it still fine for the microphone? Okay. And we can see that actually in all of the impact categories, using an electric toothbrush would be a huge environmental difference to using others as a hotspot here in the purple lines. Okay, so in the end, if you're using a plastic or a bamboo, it's much better than using an electric one. But it turns out that in nearly all of the impact categories, or actually, this was a surprise to me, that a plastic manual replaceable toothbrush is better in certain aspects in comparison to even a bamboo toothbrush. For example, water scarcity, because bamboo needs a lot of water to get raised. Bamboo has other benefits, like, for example, carbon capture whilst it's growing, etc. So basically, this is a micro example of how things could how life cycle assessment could then determine decisions. So, how to do a life cycle assessment and what really is it? Life cycle assessment looks at the whole life cycle of a product. One can do a life cycle assessment also of a specific process, also of a company, okay, etc. But looking at it in a product perspective, we look at all of the life cycle stages, and we try not to forget any of the life cycle stages. So from resource extraction, okay, to then the resource processing, manufacturing, transportation, retail and use, and then end of life, which could be disposal, recycling, reusing, etc. Trying to then give a perspective of life cycle thinking, where we try to design in order to decrease our impact environmentally, socially. We could also do, etc. And it's important to therefore look at everything, because when one does an environmental and a sustainability assessment, if you only look at your part of the process, let's say I'm a factory producing the toothbrush, and I only focus on my process to try to make it better, the overall carbon footprint of the toothbrush is not only determined by that process, but by its whole life cycle. So sometimes the hotspot is at other life cycle stage, and it makes more sense to put effort in that life cycle stage. So thanks to databases and data collection, etc., one can understand where the hotspots are in different impact categories, and therefore try to decrease the environmental impact. And that is the aim of life cycle assessment. Personally, I really like it because it's more a fact-based assessment, which tries to aim to be more neutral and tries to be more representing reality in terms of environmental impacts. So a bit how this all started. The first approaches were around 30 years ago, when no one was interested really on this. And then lately, you know that environmental impacts really have they have a big say now in project research to start with, but also at a company level, and also in marketing, because now it's really trendy to try to be sustainable, etc. But at the same time, it makes sense in order to keep continuing to live in sort of standards that we live on now. We have to make changes, and therefore we have to make assessments to understand how to change in order for the best impact. No, this is a bit information. The ISO standard 14040 and 14044 establishes the standards for life cycle assessment. From there, then other standards that are based on this ISO standard come up. Like, for example, maybe you've heard of EPDs, environmental product declarations, eco profiles. Actually, I have pictures. Yeah, EPDs, environmental product declarations for let's say for products. Of course, it's even sometimes compulsory for construction products and really looked for. It turns out that now even big manufacturers, let's say a big car manufacturer, asks their supply chain to do environmental product declarations and to do life cycle assessments, so that they can then understand their environmental impact, and so that they can then maybe choose from one to another, etc. So it's something that now is even requested by companies just because they want to meet their goals. Carbon neutral by 2030, etc. So if you've heard that, this puts pressure in doing these types of assessments. Eco profiles is really now run by the Plastics Europe organization, and then they have this interactive map where you can then click on any of these chemicals, and then you download an eco profile, which in the end is a model of a life cycle assessment, and then also has a report. Then also carbon footprint, water footprint, greenhouse gas protocol. Maybe you've heard greenhouse gas protocol really focuses on carbon footprint and then speaks about scope 1, scope 2, scope 3. Maybe you've heard about that too. But basically everything that then is a standard in life cycle assessment originally parts from the ISO standards 14040 and 14044. Okay, and so what's the output of a life cycle assessment? This is, I'm not sure if you can see it very well, but this is one output that I've run in OpenLCA. And so I've done well, I modeled a dummy model because I'm not a chemist, I'm an electrical engineer. However, one can do a life cycle assessment by doing research, and with the client, I can put together the ingredients then to do a life cycle assessment, and I put together this dummy example for a chemistry conference. And so this is the bioethanol combustion life cycle assessment results with the impact assessment method EF 3.0, which is one established by the European Commission. And so these are all of the impact categories, these are all of the results given by this mini example study that I made. So here we have climate change, which gives you a carbon footprint. Then climate change sometimes is broken down into biogenic, let's say biogenic costs, fossil and land use, let's say equivalents in carbon dioxide. Then it looks at ecotoxicity of water, eutrophication of water, human toxicity, And then stuff like ionizing radiation, so what's the radioactive impact of my study, of my product, land use, ozone layer depletion, etc. This is the most summarized, let's say, result, but from there one can really dig deep with OpenOCA and generally in life cycle assessment softwares into hotspots of the supply chain to really understand where to put the effort in. So how does one do life cycle assessment? Because I'm here today so that maybe you're interested in this topic, surely you've heard about it, and so how can you start doing it? So this is not a workshop either, but overall I'd like to show what are the ingredients that you would need for your life cycle assessment for your, let's say, chemical process or your product that you're in the end going to study, even like a comparison also. So we have two types of data. We have foreground data and background data, okay? The foreground data is the one that you will be collecting. It's called primary data, and you directly collect this data, which is specific to the model. And it looks something like this. For a process that you're investigating, you need to know things like the energy that this process is consuming, okay? Where is this energy coming from also? This is very important. Then which products are feeding inside this process and which resources also are feeding inside this process. For example, are you using land whilst you're carrying out this process? And then what's coming out of the process? So the product, the byproducts, the waste, emissions to water, to soil, to air. And so in the end, life cycle assessment summarizes in a process which has inputs and outputs and which is connected to other processes. Processes feed into each other. So the outputs of one process will feed into the inputs of the other, and then you make a chain that ends up being a model. And the foreground model is the one that you're modeling, which is specific to your process, your part of the supply chain. And then we would have the background data, because unfortunately, it's just impossible to be able to go as deep as understanding where materials come from and how is the conditions of this material extraction. So this comes with databases. Some famous databases are EcoInvent. There's also, EcoInvent is a Swiss database. It's the one that I'm using most of the time when I'm doing studies. It covers the whole world, many sectors, and it's updated regularly. In the end, your model is as good as the data that is inside your model, because in the end, this will represent the results. So it's important to use a good database, and EcoInvent is a very renowned and well-established database in life cycle assessment. Other examples, for example, LCA Commons is a US database. It's collected and put together by the US government with many sectors. There's other databases like AgriBalise, made by the French government, available for free, specialized in agricultural products and agricultural processes. So in the end, you have to find, this is the most important thing, you have to collect your data, understand your flow diagram, what goes in, what goes out. This is very crucial. And to select your background data. There's no right or wrong answer. There's many databases that you can find, and you have to really understand that this database has a good electricity mix, that it has, let's say, good transportation processes, etc., that you can just bring into your model. And then this background data is average data. Yeah, and so you connect the foreground model to the background model, in our case, with OpenOCA. So this process, in the end, has a lot of interconnections. You could do it very simply. A carbon footprint calculator could be in Excel, okay? If you are bringing in more impact categories, and if you're bringing in a more complex supply chain, you need, or it would be nice to move out of Excel into another tool. So there's many tools for life cycle assessment. Actually, that's not true. There's not that many in comparison to other software tools that you have thousands of, like boards, that you can play around in a video call. I'm sure that you have many. But I think now with life cycle assessment being more important and being used more, maybe we see more tools coming up. The thing is, to do a tool for life cycle assessment, you have to, one, understand software, and two, understand life cycle assessment. And it's something that doesn't really go together that much, and that's why there's not many tools. Green Data does OpenLCA, which we think it's the best tool for life cycle assessment. But I really believe it's true. First of all, it's, well, I can speak about it a bit later, but there's, being openly speaking, there's 3 big open lifecycle assessment tools for lifecycle assessment. One's CIMAPRO, the other one's Gavi, and the other one's OpenLCA. And CIMAPRO and Gavi are much older than OpenLCA, and that's why they're still being used in many universities and institutions, etc. We have a lot of projects where people are migrating to OpenLCA, but I'll explain a bit later. And then you get a lot of specialized lifecycle assessment tools, because in the end, lifecycle assessment is for everything, but some tools, for example, construction sector, which really does a lot of lifecycle assessment, there's specific tools for that. For example, one-click LCA is specifically for construction. I don't know about a tool that's specifically for chemistry, but that's anyways irrelevant. You can also do construction lifecycle assessment with OpenLCA. But why is OpenLCA so great? So it's an open source lifecycle assessment tool that is also available for free. So as opposed to its, let's say, competitors, which, well, it's really available for everyone to use it. In the end, the sustainable solution in order for everyone to do sustainability is that everyone can access to it. And 10,000 euros per year for a license might be a bit inaccessible for a lot of parts of the world. So OpenLCA is available for free. You download it in your laptop, and it's also not connected to the internet. Everything's secure in your machine. And then you have to import databases. I'll speak about that later. And it is the most widely used lifecycle assessment software in the world, basically because it's really easy to just download it and you can start playing with it. And it was really supported a lot by the US Environmental Protection Agency, and that's why it grew also a lot. The US Environmental Protection Agency was looking for a software that was open source to do lifecycle assessment. And so they then financed the OpenLCA project a lot. And we're constantly developing it with research projects, etc. And we're actually releasing OpenLCA 2.0, the next version of the software, hopefully in November. It's very important that you have access to as many databases as possible, because in the end, as I said, data is a very crucial part of the assessment. And OpenLCA has a lot of databases, so you have the software that you download, and this is a bit how you would do it. Then you have to import a database and a method. So the database you can find in OpenLCA Nexus, which is like the Amazon for LCA databases for OpenLCA. So what I mean is that it works like a marketplace. So you just put the database that you want in the cart, and then you directly use it. We have all of the big databases for lifecycle assessment available for OpenLCA. From Equivent, we also even have the Gavi database for OpenLCA. It's just that we're not official resellers anymore, because Gavi decided that maybe we're a bit dangerous for their business, so it doesn't figure in OpenLCA Nexus, but we still have it available. Just that you have to acquire it first with Gavi, and then we can pass it on to OpenLCA. And then you need the methods, which maps the data into results. This is very important, and we have a method package which has over 40 methods that is constantly also developed. Like the last one that was added was the IPCC 2021 with the new report. There was some corrections with the methods, and this was already implemented. And with these 3 ingredients, okay, software, database, which software's for free. Database has a price. We are database developers, but we don't develop all of the databases. So there's third parties that establish prices for databases, and then this is what you have to pay. And then the methods for now are for free also. And so then the outcome of this is a life cycle assessment, but let me also introduce social life cycle assessment and economic, let's say, life cycle assessment, life cycle costing, it's been said. Because we have been speaking about life cycle assessment in terms of environmental impacts, but sometimes maybe it's even interesting to understand the social implications of your supply chain. So if you're producing something, how much child work is being produced, is being used, how many hours of work, for example, but there's also impact categories for social assessments, which I think is really interesting. And in the end, sustainability doesn't only look at environment, but also at, let's say, the full picture, is environment, social, and economic aspects. As, let's say, a taster, OpenLCA can also be an extremely powerful tool. You can connect it to Python and to SQL for automation and also for database development. And you can also collaborate with the collaboration server with other, let's say, machines in the same model. A bit an overview, I'm not going to go entirely through this, but you can do these 3 types of assessments in OpenLCA, which is your study can be ISO compliant with OpenLCA. You can do any standard. The thing is, the LCA practitioner has to understand the standard in order to do it in OpenLCA. You can also create your own databases. You can work out carbon footprint, water footprint. You can do uncertainty, data quality, etc. Okay, and just very briefly, so that you understand the boom of LCA, but also OpenLCA, which I think is really correlated, because when people want to start something or are interested about something, maybe they try to look at what's free, free solutions. So we cannot track how many people are using OpenLCA because we don't have this information. You download it and then it's not our problem anymore, meaning that you're also very safe in your models, etc., because it's not communicating with the cloud or anything. But so that you understand, since not that long ago, the difference in unique downloads, so from 2019 to 2021, it was already twice as many people downloading OpenLCA, and then this presentation I had made originally for something in June, I think. So until May, it was already half of 2021's downloads. So that you can understand the increase. And also looking at our social media, in the last year, we had 90% increase in LinkedIn followers, and also 51% increase in YouTube subscribers. There's a lot of YouTube content that we have if you want to try to play around with OpenLCA. It's like tutorials, etc. And also really we've had such a huge trainings boost that we are now training other people to do OpenLCA training so that we can focus on research, development of databases, LCAs ourselves, and others can also start training OpenLCA in other countries also. So that was a bit the OpenLCA project. And then let me say who we are, Green Data. Maybe it's a bit more personal, but before working for Green Data, I was doing a startup in lifecycle assessment, and I was really interested in the lifecycle in the OpenLCA project, of course. And then I was already living in Berlin, and it was really amazing to me that Green Data actually is a Berlin company, and that it's quite small. We're around 20 people in such a huge project that in the end has such a big impact. So we're located in Berlin. We're around 20 people, fluctuating because we get a lot of interns also and working students, because my managing director, which is Andreas Tiro, who founded the company in 2004, he really likes fresh minds and to train people that are motivated. Therefore we have a lot of people coming for 6 months, etc. So that's why it's around 20 people. And so something interesting that we do is that it's like a Green Delta. We do tools. So we can do software for sustainability because we have the LCA expertise and the software. And then we work with data and also know-how in private projects as consultancy, but also in research, in big projects that have ranged from the US funding us to European Commission. We have some projects ranging from plastics to architecture, etc. And then, well, we have worldwide clients, partners, etc. And so a bit then to finalize our involvement then with BIOALL, we're here as the LCA expertise and to really to form people and mentor around life cycle assessment, social life cycle assessment, and also life cycle costing. And so our involvement will be more apparent and bigger in 2023. We have a plan, we're planning to go to Chile to work there with Recupac, which is a recycling company that's really working in Chile a lot. Also, hopefully with the university also there. This is maybe a great opportunity, this meeting in Seville to finalize a bit this. And also we will be hosting a couple of people in Berlin, also to do a secondment there so that they can learn how to do life cycle assessment. And also a workshop which has to be still decided if it's in Surrey or Berlin, but about life cycle assessment. So a bit to explain what life cycle assessment is, form the people in this project with life cycle assessment with OpenLCA, and then follow up with that in a mentoring type of way. So that was all, and thank you very much for listening. I thought it was gonna be a bit shorter. And if you have any questions, I'm really happy to answer. Thank you.
Thank you, Julia, for fantastic presentation. Any question in the room? Anna?
Hi, Julia, thank you very much for your presentation. It's very nice to have someone so enthusiastic about her job. So for the primary data that you get, I mean, I believe when a process is industrial already, that's, well, not easy, but let's say you have the data, but when the process would be new, something as what we do, for example, if we want to compare with something new, how do you do? How do you collect the data, or which information do you need? I mean, energy and so on.
Yes, with the new things, the point there, which was also introduced before, is that it's different to understand the environmental impact of something that's a bit pilot and lower scale to how this would be introduced in industry, etc. But already having an understanding of this pilot environmental impact, and then from there kind of assessing or upscaling the model with assumptions, etc. That's, I think, how it would be done. So first of all, to understand how it's done in the laboratory, and then to upscale it there. To compare, it's always hard in lifecycle assessment because you have many databases that you could be using, you have many methods that you could be using, and using one or the other will affect your results. So, and also the goal and scope. So if you're taking into account one thing or others, in the end, a lifecycle assessment has a lot of assumptions. So if you're gonna compare it with already an existing lifecycle assessment study, you really have to understand what they have done, what database they have used, what methods they have used, what assumptions they've done. And then you can compare. You could also directly do two studies to compare them. So if you do two studies, the advantage is that you're using the same, you know that you're using the same database for both, the same methods, the same assumptions, and then you can see. You have to have an idea of how this is gonna scale up. This is also important. But at a laboratory level, what I explained before of understanding the energy use, the products being used, byproducts, waste, etc., is very important.
Thank you.
Any other question? Sergio.
Thank you very much, Julia, for the nice talk. I have a question. First of all, I'm a chemist, which I'm for life cycle assessment. I'm a bit dumb, so and in the past years we have been in our company, we have been working in collaboration with a lot of groups, which actually they are able to do this life cycle assessment. And I have been the pleasure of working in collaboration with them. So I have a question from my point of view, because I'm a dummy on life cycle assessment, and every single time that I need to look at these numbers, I struggle. So in your opinion, you try to sell us the idea of OpenLCA software, which is a fantastic tool. How hard it would be for someone like me to learn to use it properly, in your opinion? How long?
And first of all, I'd like to say something. For me, it's more important to sell lifecycle assessment than OpenLCA, but at the same time, I think OpenLCA is really easy to then carry out lifecycle assessment. So my boss says that you don't have to have a master in lifecycle assessment, because also that doesn't exist really. It's more that you have to have a feeling for numbers and data sets. So he really says that if you're not stupid, you can do it. Really? But I'd say it doesn't take that long to learn. So if and then you're always learning at the same time. But I'd say with everything. I'd say with 1 month, you can already have a good idea. But 1 month focusing on it, you can really have a good idea. Really 1 month being there. We give the basic and intermediate course that already gives you a good idea, and then you have to practice. How I have learned also has been doing case studies. In the end, instead of... It helps because then you go through everything and you understand. It's not good to study the ISO standards, let's say. It's important to read them so that you understand what you cover, etc. But to study and write, in Spain at least, we did a lot the copying to study, etc. The book, no? This doesn't apply. So my first LCA study was, I was comparing milk, cow milk, with a milk substitute. And I did a very simple case. And this really helped me. We have case studies already made for OpenLCA. There's one that you can even do for free, and the tutorial is also available for free for comparing a PET bottle. So this introduces you to lifecycle assessment and also the software, how to create a process, how to link processes, how to run results. So yeah. Yes, you can learn it. Then having...
She can prove you wrong, Sergio.
Having someone to check your work is important, because then you could be doing something and then it's totally wrong or something. So you can do it on your own, and then have maybe your colleagues, if they're also learning with you, to discuss, etc. Or in this time that we're together, having, let's say, an hour of support or something where you can go through your questions is also good.
Excellent. Thank you, Julia.
It's not like studying chemistry again, I tell you this.
I don't think we have time for more questions. I saw some hands, but it's a quick one, very, very quick one. Okay.
Thank you for your presentation. Could the program also be used to do an economical analysis of the process?
So there's one column in the work that is for costs. So you can put the costs of the ingredients, the inputs and outputs, you can put costs. And in the end, you can run it so that then it also calculates life cycle costing. So it has that dimension also.
Excellent. Thank you, Julia. Thank you very much.
I leave this here. Thanks.
Right, so the next presentation is coming from our project coordinator, Ana Belén from Madrid. So she's the important one because she pays for the coffees and everything. So guys, pay attention to this excellent presentation.
I will be fast.
We are good with timing, by the way, so we are meant to have the coffee break 11:15, so we are fine.
This is to... Yes, okay. And the pointer is this. So, hi to everyone. Thank you for attending this workshop. I will be talking today about some of the research that we do at the group of molecular design of heterogeneous catalysts. We belong to the Institute of Catalysis and Petrochemistry of the Spanish National Research Council, and we are located in Madrid. I will be talking today about the research that we do, especially with carbon materials. So, Now the research lines related to catalysis aim at obtaining new processes with new raw materials and considering all environmental issues for that. So we need to reduce the temperature of the process, the number of operations, we need to be more efficient for that. And also considering that the price of the catalyst is about quarter of the total cost, it's really important this design, and that's what we do. So we try in our group to optimize the number of active sites of the catalyst. And we work with several materials, but mainly we are focused on carbon. And why carbon? Because carbon is a low material, is very stable, chemical and temperature stability is very high. It has a low price, and also the active phase can be easily recovered just by burning out the carbon. We work with several carbon nanostructures that we either buy commercial or that we prepare at the lab, like carbon nanotubes, reduced graphene oxides, or the benchmark of our lab, which is the high commercial surface area graphite. And specifically today we'll be talking about two research lines which are related to CO2 valorization to methanol and hydrogen production from formic acid. So we all know that the CO2 emissions which are due to human activity are very dangerous, because even though they are a small amount related to the total amount of CO2 emissions, they are critical related to the temperature increase that we have. So we need to reduce that. And for that we have several options industrially that we can do. So it's improve the energy efficiency of the current technologies. We can replace fossil fuels by renewable energies, or what we will be talking today, we can capture this CO2 in this case and convert it into something useful. And one of the strategies that we can do is to hydrogenate this CO2 molecule. CO2 is in principle a very inert molecule, but if you react it with hydrogen, it reacts more easily. One of the strategies is to make it, the reaction with hydrogen, which is produced from the excess energy of renewable energies. So in this case, you would store also the energy from excess from these renewable sources. One of the compounds that you can obtain is methanol from this hydrogenation, which is very convenient because it's relatively easy to handle. You can use it directly as a fuel in fuel cells, or you can use it as a raw material. Indeed, as far as I know, maybe there are more, but there is a small plant in Iceland which uses geothermal energy to convert CO2 to methanol. And in that case, they use the common copper zinc oxide catalyst. Most of the catalysts that are used for this reaction are based on copper. This is a structure-sensitive reaction, which means that the activity depends on the crystal phase that are exposed of the copper. And the problem with copper is that when you increase the temperature in the presence of water, it gets quite relatively easy oxidized and it sinters easily. So for that, there are several strategies like using different oxides and promoters to improve this stability. Recently, it was observed that the molybdenum carbide, copper molybdenum carbide system was much more active than the benchmark copper zinc oxide catalyst that it used. And indeed, molybdenum carbide has been used for several hydrogenation, and it proved to be very active. Its activity is compared with noble metals, even though the price is much lower. So our aim was to study the synthesis of this molybdenum carbide using carbon as support. In this case, instead of using the typical atmosphere of hydrocarbon hydrogen, we could use only hydrogen, because the carbon support was the carbon source to carbonize the molybdenum. And hence we studied the high surface area graphite that we buy commercially. And we treated well, after impregnation with the molybdenum precursor, we treated under a hydrogen argon atmosphere and followed the nearest option that we had for the molybdenum species. And we saw that indeed under hydrogen, it was possible to obtain already the molybdenum Oxy Carbide at 300, which is quite low temperature. And then upon increasing at 400, the molybdenum carbide started to be formed. And we also saw, although it's not here, that the profile of them, when we did this experiment also with methane and hydrogen, was very similar. So it means that in the end of the day, when you treat a sample with hydrogen or with methane-hydrogen mixture, actually the support is the source of carbon and not the methane that you are using. So considering this, we decided to study the effect of the synthesis temperature of copper molybdenum and molybdenum monometallic, and also the effect of copper loading on these samples, which are copper molybdenum supported on the commercial graphite. So to study the synthesis of the materials, we studied them by performing in situ X-ray diffraction under hydrogen atmosphere. And we saw that all the catalysts that have been prepared presented the molybdenum Oxy Carbide species along with some molybdenum oxide. And only in the sample with copper and treated at 700 displayed some diffraction related to the molybdenum carbide. And it was the most interesting thing for us, because we didn't see before anything in the literature, was that when you treated the samples at 700, we found some molybdenum in the metallic state. When we studied this sample also by performing the treatment in hydrogen in situ by XPS, we saw some differences. This is normal because the XPS is a surface technique, as you know. So now we also see the molybdenum metallic, but in this case the ratio was much similar between these samples than it was found by the X-ray diffraction. And now we could see that molybdenum carbide appears. So we really formed molybdenum carbide, and the ratio was higher in the samples that were treated at 600 than in the samples treated at 700. So the fact that we see here the molybdenum carbide and not in the X-ray diffraction, as you know already, is because the size of this particle is much smaller. So this means that the smallest particles are more easily oxidized and carbonized, and we see them by XPS but not by X-ray diffraction. And if we think that the support itself is the carbon source, it really makes sense, because the contact between the nanoparticle and the support is higher in the small particles. So something else that we saw that in the XPS that was a bit more surprising is that the samples that were treated at 700 actually had a larger ratio of the oxide, the molybdenum oxide. So to understand a bit better what was happening with this, we designed an experiment in which the samples were reduced under deuterium and under hydrogen. And then the sample reduced under hydrogen was also passed with some deuterium. So these samples, I'm showing here only the one with copper molybdenum, but the profile of the molybdenum monometallic was very similar. And when we heated the sample, we followed the mass that evolved, the gases evolved by mass spectroscopy. And we could see that when it reaches like 500, it was done under vacuum. When we reached like 500 degrees, there was the evolution of mass 2 and mass 3. So along with some of a small amount of mass 4. So this means that actually what we formed inside the crystal particle is some kind of hydride. And upon heating the sample, the atoms recombine. So 2 hydrogen atoms, they combine into hydrogen, and then we have atomic exchange between hydrogen and deuterium. And that's why we see mass 3. And we didn't see this behavior either in the bare support or in the copper monometallic sample. So it means that this formed hydride might be from the molybdenum. So we are not sure about if it is hydride with the molybdenum oxide, this form of molybdenum Oxy Carbide, or just with the molybdenum. So then, to study a bit better this transformation, we mimic the reduction of this catalyst. So we passed the hydrogen flow as we did in the synthesis condition. I followed the gases that evolved by mass spectroscopy. And we observed that besides some of the signals here, which are assigned to water from the reduction of the molybdenum oxides and so on, we could see at high temperature that there was the evolution of mass 18, which is assigned to water, in the sample monometallic molybdenum, and we saw the mass 15, which corresponds to methane, and on the sample bimetallic. Considering that it's probably that we had some of these hydrides, a possible mechanism that may occur is that these hydrides, These hydrides, at high temperature, they decompose and they are transformed into the molybdenum metallic that we've seen before, and they also decompose into water and methane. So, but what are the effects of all this in the reaction at the end of the day? So we compared the samples with copper and without copper, treated at 600 and at 700. And we saw that copper in both cases increases the activity to methanol, and that when we increase the temperature of this reaction, of the synthesis, the activity to the production of methanol decreased. So, well, about the synthesis at 700, we really observed that some molybdenum metallic was formed. So it was somehow expected because this monometallic, metallic molybdenum favors the formation of some intermediate species, and then the break of the carbon-oxygen bond is not favored in these conditions. And copper has a positive effect. So we decided to test some different loadings of copper. And in this catalyst, what we first saw is that the monometallic copper was not active at all, and that the yield to methanol increased with the loading of copper. So again, the fact that copper was not active could be expected because copper is formed as relatively large particles in the monometallic catalyst, and these large particles are not able to absorb and activate the CO2. And what we saw in the bimetallic samples, it was very difficult to find areas with copper and molybdenum together collocated. We mainly saw very large copper particles and small molybdenum carbide particles. So only in a very few areas that I am showing here, we could see molybdenum with some spots of copper. And these small areas were the responsible of this increase in the activity to methanol. And then we increase the temperature of the reaction to study stability. As we can see, the catalysts were very stable. And the characterization by X-ray diffraction after the reaction showed that there were some changes in the species. So while for we observed before that for the samples that were treated at 600, we didn't have the molybdenum carbide, but the molybdenum Oxy Carbide. But after reaction, the diffractions which are related to the molybdenum carbide appeared, so they have been changed under the reaction atmosphere. And the samples treated at 700 that initially had the molybdenum in the metallic form, they don't display now this diffraction of molybdenum, which was this large peak intense here, but they now show small humps in the diffractions, which are related in this case for the molybdenum oxide, and in this case with copper, we also see the molybdenum oxide diffractions, but a bit more intense. So in this case, it means that this molybdenum in the metallic form transferred into molybdenum oxide. So it's not a stable species. And also this is probably the reason because we tried to do some microscopy on this sample, and since they were exposed to air, we didn't see anything in the microscopy. So, but in any case, these changes do not affect the stability, so either it refers to species that are not active on the reaction, or maybe some other species of molybdenum carbide that we cannot see here, they are increasing the activity. So, well, this was the first part, and now I will talk a bit about the hydrogen progression that had been already mentioned before. So we need hydrogen, and we need a lot of hydrogen, and if in the future we aim at having these biorefinery schemes that probably will be like this, we will need more hydrogen to reduce these molecules. And now we produce hydrogen mainly by using fossil fuels, so we need to change this and have other alternatives. Among them, they have been mentioned that, well, the typical reforming of hydrocarbons and alcohols, metal hydrolysis, and we are now focused on the formic acid decomposition. And why is that? Because, well, formic acid would be a large biorefinery waste in the future coming from the hydrolysis of cellulose. It has a simple structure, is relatively easy to handle also because it's liquid at atmospheric conditions, and its price is low, so it can be used to obtain hydrogen instead of other commodities, for example. This reaction is thermodynamically favored, but kinetically is not. So it means that we need to increase the temperature to have this reaction. However, at higher temperatures, we also have the reverse water gas shift. So most of the catalysts that have been tested today in the literature are noble metals, but noble metals are expensive. So we try to study this by using a nickel-copper bimetallic catalyst over different carbon supports. We have used commercial supports, single-walled and multi-walled carbon nanotubes. They mainly differ in the size of the graphenic layers. In the case of the single-walled carbon nanotubes, they are much larger, and also the diameter that we have, and they are more pure. They have less activated carbon, which is quite common in the multi-walled carbon nanotubes, even if they are commercial. And for the lab-prepared supports, we normally prepare reduced graphene oxides, which are shown here. These are very large graphenic layers, both. This type of graphene, they differ in the surface area mainly. That's the reason. The N refers to the doping, so we either dope it with nitrogen or undope it. We also prepare carbon nanospheres and carbon nanotubes in the lab. And so we compared some like 2D or more or less structure, let's say, with rounded carbon nanostructures. The synthesis also differs in the fact that when we prepare reduced graphene oxide and the nanospheres, we first have a carbon precursors. We already have the carbon nanostructure with several oxygen groups, and then we dope it with ammonia to obtain the nitrogen doped samples. However, in the case of the carbon nanotubes, the preparation is at the same time, so we use a mixture of hydrocarbons and ammonia using an iron catalyst to prepare the carbon nanotubes and at the same time to dope it. And well, as I was saying before, the differences between these reduced at the reduced graphene oxides is the surface area. And the difference in this synthesis method, then we can see by the XPS, okay, that the reduced graphene oxides and the carbon nanosphere, which have been doped after we have the carbon precursor, they have a higher ratio of nitrogen pyridinic, which is this one. However, in the case of the carbon nanotubes, the larger ratio of the nitrogen species is related to the pyrrolic nitrogen. Okay? And these have some consequences in the reducibility. Well, first, related to the morphology of the catalyst, we saw that systematically all the larger the graphenic layers were, the lower the temperature of the reduction. So this can be related because the particle size was very similar of the nickel-copper particles, so it can be related to the fact that the graphenic electron helps in the reduction of the nickel-copper particles. And also related to the nitrogen samples, what we saw is that when we dope the samples, the reduction temperature increased, except in the case of the carbon nanotubes. And this different behavior was also observed in the XPS spectra of the copper. So the XPS spectra of the copper region showed that for the nitrogen samples, the binding energy of copper was slightly shifted to lower binding energy for the spheres and for the reduced graphene oxide. And this means that this copper is negatively charged slightly. But this did not happen in the carbon nanotube. So somehow the interaction between the nickel-copper particles and the support was different in the reduced graphenes and in the spheres, and compared to the carbon nanotubes. So we tested this catalyst in the formic acid decomposition, and we saw that, well, all the selectivity was relatively high, between 95 and 96%, And the calculation of the activity of this catalyst at 50% conversion showed that the nitrogen doped catalysts were indeed worse in terms of activity for this reaction compared to the undoped sample, except in the case of the carbon nanotubes doped with nitrogen. The fact that the nitrogen doped were worse, considering the previous characterization, can be related to the electron charge that is provided from the pyridinic nitrogen to the nanoparticles, because in this case, these particles are located on top of the nitrogen. If this happens and you have a particle which is negatively charged, it's more difficult for this particle to stabilize the formate intermediate, which is necessary to then decompose it into hydrogen and CO2. However, in the case of the carbon nanotubes, this type of carbon nanotubes, they have, pyrrolic nitrogen, but the thing is that these carbon nanotubes have a lot of defects. So the particles are not only located on nitrogen, but most probably located in other places where you have no nitrogen. And that's why we didn't see any changes on the, for example, on the XPS between the doped and the undoped sample. And in that case, also the pyrrolic nitrogen could act at activation site for this formic acid, although the support itself is not active on the reaction because we tested it before. And well, what we do with all this formic acid, our aim later on is not only to decompose it, but to use it as hydrogen source to hydrogenate the molecules that we like. And first we started with the butadiene molecule because it's a very, relatively easy molecule to work with. It's a gas. It comes from petrochemical, although it may also come from other biomass transformations. And we tested palladium particles supported on different carbon nanofibers. And we saw that at 100% conversion of butadiene, it was indeed possible to perform the tandem hydrogenation. So we feed butadiene and formic acid together, and we obtained butenes and butane in different concentration, along with CO2 from the formic acid decomposition and a small amount of the remaining hydrogen. So we saw that it was possible to have this reaction in the gas phase, and also that indeed the selectivity to butenes, which is what we are looking for, is higher when we use formic acid. So far, we have explained this because during the decomposition of formic acid, you also produce CO, and this CO is a poison. So if you poison the most active sites of the palladium, maybe you can increase the selectivity to the partial hydrogenation. So after we worked with butadiene, which was an easy molecule, we started to work with furfural. Furfural is a bit more difficult to work with, but nevertheless, we managed to have some good results also in gas phase with furfural. It is so far, this slide is a bit dense, but furfural is the only molecule coming from biomass that is currently produced industrially, and the main product that is of industrial interest is the furfuryl alcohol. So for that, we use a bimetallic catalyst now, supported on the high surface area graphite. A bimetallic catalyst, this is still patent pending, so I was supposed not to say the metals, but it's one metal with a high hydrogenation ability and the other low hydrogenation ability, and they are non-noble metals, no? But just guess. So we compare the results of the conversion and selectivity using the graphite and the silica. So first, one more, also, and I forgot to mention here that always we kept the ratio of the formic acid to the reactant in a way that we had excess of this hydrogen to the reactant molecule. So we did observe that these catalysts were active and that were selective to the furfuryl alcohol production. And comparing just the supports to prove that carbon had no good support for this, we saw that even though the conversion initially it was a bit more difficult to reach the steady state, then conversion reached above 50% and it was stable. But when we use silica, the conversion started before, but it decreased and it deactivates quite relatively fast. So overall, as conclusion of this, we saw that carbon can be used as support and also a carbon source for the molybdenum carbide, that nitrogen doping influences the nanoparticle support interaction as well is influenced by the graphene layers, and that carbon can be used as potential supports for reactions with formic acid as hydrogen source. And we are still working with other tandem hydrogenation reaction, also using formic acid and CO2 to light olefins. Thank you for your attention.
Thank you, Anna. And good luck with the patent. It's looking promising, really. So, any questions in the room? Yes.
Anna, I have a question concerning this molybdenum Oxy Carbide phase. So we have a running project on the hydrodeoxynation of lignin pyrolysis products, where such molybdenum Oxy Carbide phases are considered to be the active phases, but these species are very poor defined. Yeah, so it's also the case that this is formed under reaction condition, but it depends very much on the composition of the gas phase and temperature, and in principle the formation of this phase is not very well understood. Did you try to purposefully change the reaction conditions to prepare this phase, and is there any opportunity to identify the structure, to know what we have in hands?
I would like to, but the problem we have, I mean, carbons are very nice and you want to love them, but indeed, as you know, it's very difficult to characterize them by the common techniques that we have. In operando is basically impossible. So we had not the opportunity. Maybe if you use a bulk, so we can only characterize the fresh catalyst and the spent catalyst. That's our tools that we have. But actually, the formation of this, they depend on the support, because we tried this high surface area. So there are many parameters that affect, but when you use carbon nanofibers, we didn't see this molybdenum, for example, in metallic form, or we saw different ratios. So for us, it's still the thing that is happening during the reaction is, but actually the atmosphere changes, because when you treat it under hydrogen, you have molybdenum metallic. But when you have CO2 and hydrogen, you get more molybdenum carbide. So maybe you can help us with this if there are some techniques, but still we only have the input of before reaction and after.
Yeah,
not.
Yeah. I only know a very few papers where they analyze this phase by XRD and they try to form this, but in our cases, XRD is very, very poor because particles are too small or not.
Yes, that's the problem.
But
particles of, indeed, even if they do X-ray diffraction, they lose a lot of information. As you can see, we didn't see molybdenum carbide by X-ray, but we saw it by XPS. So we need to work a bit more on that still.
Yeah, it would be very interesting to see your
but
progress
also
here.
The active phases, it has been suggested, but we cannot prove it, that you have both phases are active and they are working in a redox state somehow. So molybdenum Oxy Carbide changes into molybdenum carbide and then back so in the presence of hydrogen.
Okay, thank you.
Thank you, Angelica, for the question. Any other last question before we move to the coffee break to recharge some batteries? Well, if not, we thank Anna again for the fantastic presentation. Right, guys, coffee break just down this door to the corridor. Oh, the other way.
It's circular.
Rafa, you're working in the background. You can join us if you fancy for a coffee, huh? You deserve it. Vamos a quitar esta.
Estará en esto también, ¿eh?
Ah, pues genial, mira. 2 por 1 y viene Melis y ya. You've got a stick drive, Melis, or you want me to...
I do not. I was thinking
You want to you want to use the Mac? You want to use your computer or?
If I can, but I don't know if there's the connection available.
It's
It's a USB-C.
No, it's HDMI.
Okay.
It's good. I have an adapter for Mac.
To you, by
Yeah,
any chance?
yeah,
I don't
sure, sure. Dale caña. ¿Vale? All right, so hope you guys enjoy the coffee break. And we are going to continue with the program that we have 3 more talks and then back to lunch. So yeah, not that hard. Okay. So the next presentation is coming from ITM, Colombia, and it's going to be presented by Manuel Romero. Thank you, Manuel. The floor is yours.
Thank you, Thomas. And whoops, fue muy alto. And thank you, everyone. As Thomas says, my name is Manuel Romero. I came from ITM in Medellin, in Colombia. I'm from Spain, but now I'm working in Medellin, in Colombia. And I want to talk about effect of promoters on CO2 methanation using oxidic supports. Well, it's well known that in CO methanation reaction, the support has a very important role, mainly in CO2 absorption. And this is the reason because different synthesis methods, the mixture of different oxides and different promoters are being investigated. The more studied element or metals are alkaline and alkaline earths, and the more reported promoters, and the more reported effects are the modification or electronic structures and the increase in the basicity of the support and oxygen vacancies. However, the effect or the incorporation of the promoters in the catalyst is variable, and no consistent results have been established in reported investigation. Only a few examples of the effect of different promoters in different catalysts. In nickel alumina, when using magnesium and calcium, a slightly increase in basicity of supports is observed, but the selectivity is higher to CO, and also the formation of carbonates and higher stability against sintering. And with strontium and barium, the increase in selectivity to methane and increase in oxygen vacancies. In ruthenium zirconium catalysts, when using promoter lithium, sodium, and potassium, the authors observe the increase in charge density in the metal support interface in this order: lithium less than sodium and less than potassium, and increase in CO2 absorption and conversion. But however, the highest activity is not with potassium, it's with sodium. And this is an idea. The promotion is not caused by a greater CO2 absorption. And in other studies, is also a negative promotion with in rhodium alumina catalyst with potassium and barium. They observe that activity to methane and activity and selectivity to methane decrease with this promotion, and also worse absorption and the CO2 and hydrogen dissociation is observed. This is only a general idea, but more specifically, I want to talk about research is now in progress. Is a collaboration, obviously, inside the project. PhD student Sebastián Cisneros and Dr. Javor Amdallah have met from, and obviously Professor Angelica from LICAD, myself and PhD student Lorena Santa from ITM, and Laura Quintana, PhD student, and Ana Belén from ICP. And this research is the effect of magnesium oxide as promoter in the methanation of CO2 over ruthenium zirconia catalyst. We prepare 2 supports, zirconia and magnesium oxide zirconia, by precipitation and co-precipitation, and we include only 1.5% of magnesium. The metal load is 0.5 for ruthenium by absorption during 3 hours at room temperature, well, dry and calcination as usual. These are the reaction conditions. The pretreatment of the catalyst just before the reaction, 30 minutes in air and 140 degrees. and we study the stability, the activity and stability. The activity test, no difference were observed at low temperature, up to 200, well, low, more or less low, up to 220 degrees, but at 250 and 300 degrees, we saw the catalyst with magnesium oxide saw a higher activity than only with zirconium. And the stability, we saw that the activation started earlier when no magnesium oxide, only with zirconium, but with magnesium oxide, a longer induction time is necessary to get the maximum rate in conversion. But also, we saw some deactivation in this catalyst. Then we characterize the catalyst. First, the metal content. In both cases, the metal content of the catalyst, the ruthenium is 0.4, very close to the nominal load, and magnesium is 1.5. Yes, in fresh and before and after the metal incorporation. And the textural properties, no difference in pore volume and pore diameter, but in a specific surface, when we incorporate only 1.5 of magnesium oxide, 50% more of BT surface area is observed, and no difference between the supports and the catalyst with the metal. Very, very similar results. The X-ray diffraction, we saw a big difference because in the zirconium support and catalyst, monoclinic structure is observed, but with magnesium oxide, the structure is tetragonal, zirconium, and in this case, we saw small peaks of ruthenium oxide, and in this case, it's possibly overlapping with the zirconium signals. The TIEM microscopy, this is fresh and used ruthenium zirconium, no magnesium oxide, and we saw in this in fresh catalyst a big ruthenium oxide particles, and after reaction, the particle is mainly metal ruthenium, and also we saw more or less heterogeneous particle size in used catalysts. Here the particles are bigger, and here between 5 and 2 millimeters, more or less. This is more interesting with magnesium oxide. First, we saw a homogeneous distribution of magnesium in all the catalysts. Here we can see the magnesium. And it's also very interesting because we saw ruthenium is preferentially in magnesium-rich regions, because in these regions is zirconium, here no, but here is magnesium and also ruthenium. And in used catalysts, this is the original pictures. In this region is no zirconium, is magnesium, and here is also ruthenium. Then this is, I don't know, but more or less an idea that ruthenium support interaction is favored by the presence of magnesium oxide. And here, with this catalyst with magnesium oxide, also before with the fresh catalyst, the particles are ruthenium oxide, and after reaction are metallic ruthenium, and more homogeneous particles is observed. In TPR, we saw two main signals. The first signal is the reduction of ruthenium oxide, And we saw only with zirconium, the signal appears between 100 and 230 degrees. And with magnesium oxide, this signal is between 200 and 350. Then is necessary more temperature to reduce this ruthenium. And this maybe because more interaction, ruthenium support in presence of magnesium, as we can see also in T microscopy. And the second signal we think is very high temperature for ruthenium, and it's probably the support reduction. Here the support show no reduction, but here the hydrogen is activated by ruthenium and can reduce the support. XPS spectroscopy, we saw two main signals in ruthenium 3P. The first catalyst, both show signal at 463 electron volts, indicating ruthenium oxide, and usage catalyst, the signal is a lower value of binding energy at 261.7 electron volts, indicating metal ruthenium, and the intensity of the signal is larger with catalyst with magnesium oxide, and then is an indicative of more ruthenium on the surface and probably more dispersion of this ruthenium in the surface of this catalyst. Infrared spectroscopy in the carbonyl zone, we saw two main signals. One between 2064 and 2058 is caused because for CO carbonyl absorbed on terrace sites of ruthenium nanoparticles or the carbonyl species, and the other signal is caused because for linearly absorbed monocarbonyl species, and the signal are also in ruthenium with magnesium oxide catalyst, but the wave number decreased, indicating local change intensity of ruthenium nanoparticles. This is, if this particle is with higher local change, this bond has higher electron density, and this bond is weaker, and this can do easier the hydrogenation of the carbon. And it's very important to show also at higher temperature, 250 and 270, the intensity of this signal are higher in the presence of magnesium oxide, and indicating a greater availability of reaction intermediates in this catalyst with magnesium oxide. Continuing with infrared spectroscopy, we saw formate group in both catalysts at this signal, but the main difference is with bicarbonate group, because in the catalyst with only zirconium, we saw a small signal, 1450 here, and with magnesium oxide, this zone, the signal is higher, and also this is more clear in higher temperatures, because the signal or bicarbonate is higher here than here, and also the methane signal, this is higher in catalyst with magnesium oxide. This indicate an possible extra intermediate. The bicarbonate is an extra intermediate of this reaction in this catalyst. And finally, the reason we thought for the promotion of CO2 methanation with magnesium oxide, maybe increase the surface availability of ruthenium, probably favored by greater interaction magnesium oxide ruthenium, increase local charge of ruthenium nanoparticles, making more easier the hydrogenation of the carbon, and also produce bicarbonate and extra intermediate, mainly at higher temperatures. The reference we are using for this work. And finally, thank you to European Commission, obviously to LICAT, ITM, and ICP for academic, technical, and economic support. Thank you.
Thank you. Thank you, Manuel, for this beautiful presentation. I think methanation is back to popularity with the current situation in Europe and the gas supply, right? Mm-hmm. So maybe, right, so any questions in the audience? Luis?
Thank you very much for the presentation. It's very nice. But I had one question with the proposal of bicarbonate at temperature higher than 250 degrees. Not is very, so it is a temperature very high for the stabilization of bicarbonate on the surface. In fact, regarding the spectra, with the bicarbonate, normally appear one band 1225 more or less, that this is the bending wedge, and here is not clear, so I'm not sure that this is bicarbonate species, no, in the designation.
Probably because, as I say, this research is in progress. We have to check, because we saw in some reference this band is associated with bicarbonate species, but we will check for this weight number, because I don't know. I don't know, because we are just studying the infrared spectroscopy, and is operando, bueno, no operando, it's more or less operando, is in situ, and we have to check.
Okay, thank you.
Thank you.
Thank you, Luis. Angelica, please.
Yeah, thank you very much for this nice presentation. I have two questions concerning, the first is concerning the BET surface area. So in your magnesium containing catalyst, it was, I think, 120 compared to 75. So that is almost twice the surface area. Did you try to normalize the activity on the surface area to see explicitly the effect of the ruthenium?
Yes. I saw conversion, yes, but we have, I don't have here, but I can show you obviously. This picture, no CO2 conversion, is methane moles per moles of ruthenium, and the difference is more or less the same.
Okay. And the second question, in the adsorption of CO to characterize the ruthenium, there were two bands. How can these two bands be assigned? This would indicate that you have CO adsorbed in two different modes.
In which?
Your drifts, CO
okay.
adsorption.
Yep.
Yes, here. So how do you assign these two bands in the 2064 something and the second one 1987? So this should correspond to CO adsorbed in two different modes. How can this be explained?
The same. Sorry for this explanation, but the same explanation that we are studying with Sebastian and Javor. More clear explanation about this.
Yeah, perhaps it would be worthwhile to think about this again, because when I look on your spectra, in the zirconium-only catalyst, the band
yes.
at 20, the first one at the higher wave numbers is more intense than the second one, and it's the other way around when you add magnesium. And now it would be interesting to know how these two bands are created, which species are hidden behind. That could also give some information about the nature of the ruthenium surface.
Yes, it's true. We are studying this. Sorry for the answer, but it's the truth. We are studying just these days with Javor and Sebastian and Lorena in Colombia about the explanation of this.
Yeah, I'm keen to see the results.
Yeah, sure.
Thank you, Angelica.
But the particle size is more or less similar in both catalysts. Yes. No big difference between both catalysts. Yes.
Okay. Grab the mic so we can follow it.
Are you using nitrates for preparing the catalyst? Ruthenium nitrosyl nitrates and then magnesium nitrates?
No.
No? What are you using?
Ruthenium chloride.
Chloride.
Yes. Is for avoid the use of nitrate.
By the second peak at the TPR. Have you followed the mass spec of the gases that gets out?
No.
You should.
But we are using
because
ruthenium chloride.
Such a high temperature, sometimes it's observed with ruthenium and alkaline and so on, due to the composition of other salts.
Okay, we will check. Thank you.
All right, Manuel, thank you for sticking to the time and for the beautiful presentation.
Thank you.
Thanks. Right, the next talk is coming from my beloved University of Surrey, and it's going to be presented by Melis Duyar. So, Melis, we're going to help you with the Mac, right, to swap the computer.
Okay.
I think we got the IT team is coming, don't worry. Okay. I believe Rafa is coming.
Yeah, don't trust me with IT.
No, don't worry. So, Rafa is going to help you.
No, I should be fine. I just need to switch. This one I can keep.
Yeah, no, it's okay.
There we go.
Okay.
All right, thank you.
Okay.
I have a feeling there's a bit of a loss of connection sometimes. Let's really get to it. Okay. I might have to act out this presentation if this keeps happening. Sorry about that. Let's try again. Give it a minute. Okay. Perfect. Thank you. All right. Good afternoon, everyone. Thank you for bearing with me while I set this up. Should I stay here? Okay.
For the pointer.
Okay. All right. Thank you. So my name is Melis Duyar. I'm from the University of Surrey, pictured here in one of the most beautiful parts of our campus. And we have actually, even though I come from the University of Surrey, we have been working together with University of Seville for a long time. So I feel like I've been looking at all the data coming out of this university, and it's a big pleasure for me to finally be here. So just as a thank you for inviting me over here, I want to kind of start by showing a little bit about our department back at Surrey. We have a lovely department with about 300 undergraduates, 50 PhD students, although this year I think it's quite a bit more. And in fact, we have 3 of our PhD students who are on exchange here this year, so they're sitting at the back there. So we have a number of different programs focused on, we have a good focus on energy, but also things like healthcare as well. But today I'm going to be talking about some of the work that we do in my lab and in the Department of Chemical and Process Engineering, which is focusing on sustainable technologies for energy and environmental pollution prevention. So the title of my talk today is about, achieving circular carbon economy through the use of dual function materials, but also looking at some of our emerging work on plastics valorization. So before I get started on this, I want to kind of give an overview of some of the other activities in my group as well, because they're all connected through this theme of sustainability. So one thing that I will be talking about today is this concept of dual function materials. It's a big focus of my group. It deals with designing catalytically active materials that are also active for carbon dioxide capture. We'll see why that's important in a moment. We also work on tandem catalysis, which was mentioned a few times today. The idea there being, can we devise multi-step catalytic approaches to achieving higher selectivity or higher activity towards certain desired reactions than we could by means of designing, let's say, a bifunctional site on the same catalyst. Of course, we are always looking for these CO2 hydrogenation catalysts, because this is, I think, ultimately what will achieve great advantages in the switching to net zero economy, because we need to be comfortable with building up from these smaller molecules, building blocks, to get all the various chemicals that we rely on as a society. And then finally, an emerging area in my group is plastics capture and upcycling, and I'll talk a little bit about why we need to capture plastics and why we're talking about upcycling. So let's start with the carbon dioxide capture aspect of my talk. We know that there's a great variety of CO2 emission sources out there. So we know that these range in concentration, these range in impurities. What I'm going to start off by talking on is that there is a distinct materials challenge associated with the need to decarbonize various sectors or the need to move to net zero economies. This is because while we do have conventional means to capture carbon dioxide, we are familiar that there exist absorption-based systems that can be commercially deployed right now to capture carbon dioxide. There's a number of drawbacks which might make them not as suitable for every single application for CO2 capture that we're interested in. And especially this presents an energy cost to carbon dioxide capture and utilization processes in particular, because we are relying on toxic and corrosive absorbents which need to be diluted with a lot of water. To regenerate the absorbents, we are expending a lot of energy. So this is what motivates us to look more carefully at carbon dioxide capture and to combine that with some of our work on developing new catalytic materials to find new synergies that might make the overall carbon capture and utilization scheme more favorable. So this is a cartoon to show what circularity means in relationship to chemicals production. And I've titled this, Catalysis will enable a transition to a low carbon economy. This is because I work in catalysis, I love catalysis, I think it is the solution to all our problems. However, we're not quite there yet. So one thing that we can imagine is with the carbon cycle, we are taking a lot of carbon from underground, and through our use of this carbon, we are releasing it into the atmosphere. We all know this accumulates, causing climate change. But what can we do is that if we devise systems that are based on carbon captured from the air, now they could be biorefinery type approaches, they could be other engineered systems for carbon capture and utilization, then this closes the circle. Because no matter how we use that carbon downstream, at least from the perspective of that carbon atom, if it gets released back into the atmosphere, this is a closed circle. Now we need to be careful here, and this is why I put this green hydrogen here, is that we don't have a lot of room to generate carbon emissions in the process of synthesizing chemicals if we want to go to net zero. Similarly, we can consider the nitrogen cycle. This is not something that I'm going to be talking about today, but also here we supply a lot of our agricultural nitrogen needs from fossil-based fuels, which don't really need to be there from a chemical standpoint. We can consider closing the nitrogen cycle as well in this way, removing some emissions in the process. So while I've titled this slide, Catalysis will enable a transition to low carbon economy, I want to kind of retitle it as we need new catalytic processes to enable a transition to a low carbon economy. And why do we need new catalytic processes? There are distinct challenges associated with both the materials but also the supporting infrastructure that we need to overcome. So on that note, I will mention 3 different kind of case studies that we are looking into in our lab at Surrey and beyond with our collaborators, which is to look at the issues associated with, one, the availability of renewable hydrogen, which right now is not abundantly available, and how we might think about addressing changes in the supply of reactants we need to convert carbon dioxide, as well as maybe the changes in demand of the products that we are targeting now. This is what I will title Switchable Catalysts in this talk. I'll also talk about the fact that we don't have a global infrastructure for distributing captured CO2. So even if we were to implement CO2 capture to every emission source, we don't really have a way of getting it around to where it can be utilized. So this will lead us to the discussion around dual function materials. And then finally, I want to mention new pollutants, contaminants of emerging concern, the plastics pollution, which we will have heard of. Now, plastics problem is part of the carbon cycle because we know that we cannot let plastics accumulate in the environment, but if our solution is to make fuels from them that will get combusted, if our solution is to combust them directly, then that all of a sudden becomes a huge part of the carbon cycle problem. So I will include that, some of our preliminary work on that area in today's talk as well. So let's start with this concept of switchable catalysts for syngas and synthetic natural gas production. This idea of switchable catalysts was developed by my colleague Thomas Ramirez Reina, who's sitting here, but also this data that I'm showing today is produced by Angie Mercury, who's sitting right over there if you want to talk to her later. And what we recognize with these switchable catalysts is that there are a number of catalytic formulations that are active for methanation at low temperatures and reverse water gas shift at high temperatures. So these 2 reactions, and I'll show the equations in a moment, they're both reactions of carbon dioxide and hydrogen, thermodynamically speaking, and we're showing the equilibrium over here. We have methanation that is thermodynamically favorable at low temperatures. It's an exothermic reaction. We have reverse, at some point, our selectivity will switch over to CO production rather than methane because the reverse water gas shift becomes thermodynamically favorable. Now the catalyst allows us to reach thermodynamic equilibrium compositions at fairly low temperatures, well, reasonable temperatures, let's say. But we see this switch over to in selectivity. Now, why might this be useful? The reason is that we are now, this thinking around actually do we need flexibility in the chemicals industry if we are to use CO2 as a feedstock? And the reason why we might appreciate flexibility in CO2 utilization is actually due to the fact that we might have switching in terms of demand for various products over seasons, but even over years. So we were driven to think about this concept of why we want to make synthetic natural gas. Okay, synthetic natural gas can be directly used to replace natural gas. It can be used as residential fuel without significant alterations of infrastructure. We like this idea. But we have a demand associated with natural gas for residential purposes. That demand is going to be higher in the winter or wherever it's cold. And it's going to be lower in the summer. So you can use this to balance out renewable energy productions in certain areas. If you have higher production in the summer, you can make hydrogen, you can convert that to methane, you can distribute that, and so on. But there is a seasonal shift associated with the methane demand. And we were thinking maybe with these catalysts, we can manage our production to meet the demand specifications of the market at any given time. So what can CO be used for, or syngas, in this case through reverse water gas shift? Syngas can allow us to feed CO2 to the broader chemical synthesis arena, so to speak, and allow us to produce liquid fuels through Fischer-Tropsch type processes, and that's also useful. So we have the opportunity to make two different kinds of fuel, liquid fuels. In one instance, we can also make synthetic natural gas, and maybe with this switchability, we can balance out variations in demand for both. What's more is that the same catalyst can also, we found, perform the dry reforming of methane. Now this becomes important because right now it is quite difficult to scale up processes that rely entirely on renewable hydrogen. And one consideration that needs to be made is that can we use alternative reactants to reduce the CO2 rather than hydrogen? There are numerous groups looking at the use of hydrocarbons, reactions of hydrocarbons with CO2. In this case, we're looking at the dry reforming of methane, which produces, again, syngas, and that can be really useful. So what we're envisioning here is that if we have access to methane right now, we can already lower the carbon footprint of certain fuels by making syngas. Gradually ramping up renewable hydrogen access to the facility, we can switch over to reverse water gas shift. And if we need to supply the demand for natural gas in a pinch, we could easily perform the CO2 methanation reaction on the same catalyst. And these are nickel ruthenium catalysts supported on Syria alumina. They are showing good stable activity over numerous hours of operation. Here is an experiment that was carried out showing methanation at 350 degrees Celsius, very stable activity. We then raised the temperature to 700 to perform reverse water gas shift reaction, again, quite stable activity. At the same temperature, if we switch the feed to methane, then we can perform dry reforming. Although we have a slight issue with deactivation, there is a stable region that we can envision operating the catalyst in and then exploring regeneration, because this is likely due to coke generation, which can be reversible. So that's what we have been looking for in terms of, that's one of the ways that we have developed new catalytic materials to address a distinct challenge associated with transition to net zero. Another aspect that we need to consider is, with the switchable catalyst, we are accounting for availability of reactants. So availability of renewable hydrogen versus methane in the short versus long term, but also the change in demand for various products. Now there is this catalyst works, there is an implicit assumption there that we already have access to concentrated CO2, which has been captured, it has been transported to our facility, and we can directly feed it into our steady state catalytic reactor. This, again, is not something that we should take for granted because we don't really have the distribution network needed to just tap into a CO2 line at any given location. So that brings me to my second materials challenge associated with this sustainable development goal, which is the availability of carbon dioxide. Now, do we need to, we can see that there's different concentrations of CO2 available. CO2, we have too much of CO2, but at the same time, we don't have enough CO2 because we need to purify this. So we can look at coupling any given reaction to a source of CO2 emissions, where we implement something like a amine scrubber with regenerator. It's a whole unit that we run next to our catalytic reactor. which might be very feasible for some of these scenarios, which need to already implement, for stationary emissions, we already will need to implement some form of CO2 capture solution. So we could potentially couple our reactor to that CO2. But on the other hand, we can also consider directly coupling CO2 capture with the catalysis. And the logic behind this is that we need to develop new materials for CO2 capture. This amine absorption system is quite energy intensive. And then when we look at the steps that we take to utilize CO2, I believe that it makes sense to couple these two processes, because we capture the CO2 in the conventional system, we input energy to then release that CO2, and then we feed it into another reactor, which we need to again input energy to convert that CO2 to a useful chemical. So what we have proposed with these dual function materials is that once we capture CO2, if we capture it on a solid adsorbent, we should achieve its direct transformation. And instead of releasing a concentrated stream of CO2 that needs to then be transported, what we can do is release a concentrated stream of the chemical that we're actually interested in making. And this is the concept of dual function materials that we have been developing since I was a PhD student in Bob Farato's lab. In 2015, actually, we started presenting our results on these materials. And it's made quite a bit of improvement since then, but the basic concept remains the same. Is that we have, in this case, I'm showing what we would do in a stationary emission source, but of course we can take directly air as well. If our CO2 capture component has a high enough affinity for CO2, then we can use air. So we perform a two-step reaction in the same reactor. So we capture the CO2 first from the emission source, and then we shut the stream off and then expose the material to our co-reactant, which will then react with the CO2 that's already been captured. We are able to do this because the material has both a catalyst and an adsorbent component. So what we envision here is that the CO2 has been captured under emissions sources conditions. And then next, when we expose it to, let's say, renewable hydrogen, we get a bit of transformation of CO2 to any chemical of interest. And if that transformation is releasing energy, all the better, because that then becomes an isothermal system where we're desorbing more molecules of CO2 from the adsorbent, reacting them on the catalyst. And what we see is actually in the second step, we should get a purified product of chemical reaction rather than the CO2. So we have now done two things in the same reactor, and there's also some benefits in terms of mass and energy transfer while we have been doing these. Now, a closer look at some of the, what the data will look like, and also just to give a brief history of how we started developing these materials. We started out by looking at nano-dispersed calcium oxide, which is basically just calcium oxide supported nanoparticles of calcium oxide, and using ruthenium as a catalyst in the first instance. We supported these on an alumina support because we were targeting the methanation reaction. And what we can show is that we feed in a mixture of CO2, nitrogen, oxygen, water, whatever, and we can capture CO2 until the breakthrough point. So once we have done CO2 capture and we know that the material is saturated with CO2, what we immediately do is to purge with inert gas. This is due to the fact that we want to make sure that we can prove our hypothesis, that we are only reacting the captured CO2. So we purge with inert gas until there is no CO2 detected anymore. So any CO2 reduction product should come from only captured CO2. Next, we expose it to hydrogen. In this case, depending on your data analysis method, you might get a continuous curve, or you might try to get as many points as you want. But ultimately, what we see is a peak of methane coming off of the dual function material. So we have captured CO2, we have released methane, which is great. And methanation, being an really exothermic reaction, is actually helping us along, because what we expect is happening is that in the first instance, we have CO2 adsorbed on calcium oxide sites, maybe some on ruthenium sites, but as we're hydrogenating the CO2, we're releasing heat that then drives some spillover of the remaining CO2 molecules from adsorbent to catalyst sites. So thus, at the end of this two-step reaction, we have regenerated our adsorbent. So we have completely eliminated the step of regeneration of that is kind of necessary for all the conventional CO2 capture systems. And we have simply done it by reaction. This is the kind of first data that we obtained on this project, showing that we can actually capture CO2, which is shown by the white diamonds here. We can generate methane, and we can do this over 20 cycles without deactivating the dual function material. Now, this experiment was done under dry flue gas, synthetic flue gas conditions, which basically means we were looking at CO2, oxygen, and nitrogen. It's quite interesting that we can actually do this in a stable fashion because, we expect ruthenium to deactivate when it oxidizes. And it's actually not trivial to be able to do this reaction because we are constantly switching between oxidizing and reducing conditions. The material might change, the material might deactivate, but we are not seeing this in the case of the first materials that we synthesized. We actually then moved on to look at comparing wet versus dry conditions because you maybe don't want to remove the water that's a product of combustion. And again, we see some fluctuation when we have water in there. I think that might honestly have to do with the way that I was generating steam at the time, but really you can still perform 20 cycles of capture and methanation under both dry and wet flue gas conditions. And so you can envision that while we are not operating continuously, we could start to design processes that constantly supply you with methane using only your emission source of CO2, which is dilute CO2, without the need for purification. And if you have access to hydrogen, then that's great. You can do this repeatedly and in a stable fashion. Now, when we look at these materials, another part of this project that I want to emphasize, which is illustrated really well by the plot that Angie has made here for our review paper on the subject. What we can look at is, I mentioned this fact about we have regenerated our CO2 capture unit at the end of our methanation cycle. This is quite important because when we look at similar adsorbents, which are alkali metal or alkaline earth metal oxide nanoparticles supported on alumina, we can see that you have a certain initial adsorption capacity, and then we're plotting here the CO2 released or methanated versus how much was captured. So basically, what this plot is showing you is that you want the initial CO2 adsorption capacity to be high, but also at the end of your cycle, which is either regeneration or methanation, you want to end up with having regenerated all of your adsorbent, or as close to that as possible. What we always see with these adsorbents is that while the initial CO2 capture capacity of the bare adsorbent might be on the low side, and they have varying degrees of regenerability, when we add a catalyst to the same adsorbents and perform methanation instead of desorption, we always get better regeneration of the adsorbent because of this heat of methanation that's driving this cycle as well. So long story short, this is a pretty good way to ensure that we are able to regenerate the adsorbent as well. Now, how do we combine this with the need for flexibility in the chemical industry, which I tried to make a case for in the first part of the presentation? What we have done now is to see if we can make switchable dual function materials. So we know what happens when we perform methanation in this mode, but what if we were to perform other reactions, reverse water gas shift, or dry reforming of methane, considering that we might not necessarily have access to renewable hydrogen or the need for methane at that particular time of the year. So we are going back into this mode of how do we engineer dual function materials. We have the perfect catalyst to be able to do all three of these reactions. I've already shown you the results from that. Let's talk briefly about the adsorbent. The adsorbent is quite important because, as I said, when we are running the reaction on the catalyst, switchable catalyst, we are no longer going to be having a steady state stream of CO2 entering the catalyst bed. So now we are only relying on the captured CO2, which means the strength of that bond of CO2 with the surface is going to influence how well we can generate chemicals in this mode. So what we are interested in for dual function materials is to lie in the sweet spot of chemisorbed CO2. This means that it's reversible adsorption of CO2 in several hundreds of degrees Celsius. So we can capture CO2 quite in a strong fashion. It will stay stable until we reach the reaction temperature, but it will be reversibly adsorbed so that we can actually use it as a reactant. So that's why we're interested in designing chemisorbents for dual function materials. And this is exactly what Angie did, is to use some of the promising sorbents that work in the same temperature ranges as the switchable catalysts, and to combine that with the nickel ruthenium Syria alumina support. So we're looking at sodium, potassium, and calcium dual function materials in the next slides. Now, one thing to keep in mind is that while these adsorbents have been tested for methanation conditions, the dry reforming and reverse water gas shift take place at really higher temperatures than the methanation reaction. So we still need to make sure that there's some stable CO2 on the adsorbent materials at these high temperatures. So by performing thermogravimetric analysis experiments, we can measure the CO2 uptake over multiple cycles. You can see each color represents a different adsorbent that we were looking at. Actually, this is the one for dual function materials, so adsorbent and catalyst. We can see the sodium in red, potassium in blue, and calcium in green. And when we go from 350 degrees all the way to 650 degrees, we still see that the materials are able to reversibly capture CO2, which means that we should be able to perform a reaction on them. So have we managed to do it? Yes. We have actually managed to show that we can perform all three reactions from captured CO2 only by just switching the temperature of operation and the feed gas. So what we're showing here is for the different dual function materials that we have made, we are showing basically the products that we are observing during the reaction cycle. We're not showing the CO2 uptake on this plot yet. And what we can see is that basically what we have done is we have done 3 cycles of operation. So first one was CO2 capture at 350 degrees, and then methanation with hydrogen. We then raised the temperature, captured CO2 again, performed reverse water gas shift, and then we performed CO2 capture again at the same temperature, but this time switching to methane rather than hydrogen, and we were able to perform the dry reforming of methane. Now these have varying activities they don't have the same activity for all 3 reactions, but there is room for further optimization of the reaction conditions. So for example, we can explore more dynamic CO2 capture and reaction modes. And then one other thing that was really striking that we observed on these materials happened when we were performing hydrogen temperature program reduction of the as synthesized dual function materials. Now, you can see in this dashed line, this is the temperature program reduction profile of the nickel ruthenium catalyst by itself. And when we detect, the water mass signal, we can see the reduction of the various metal precursors, and we don't detect any other product. The situation is not the same with these dual function materials. We actually see the reduction of the metals again, but once the metals are slightly activated, what we actually see, which is striking, is that these air-exposed as synthesized materials are producing carbon monoxide, and they're also producing methane. Now, we did not perform an active CO2 capture step on these. They were exposed to the ambient air. So this shows that we can actually synthesize products directly from the air. And we see some differences in selectivity, and we believe this is due to the various carbon dioxide adsorption sites that are available. So the strength of CO2 adsorption affects the selectivity. Maybe the interaction with calcium, potassium, sodium with the nickel-ruthenium affects selectivity. This is now what we're trying to find out. I'll speed up a little bit to get through the final part as well. Basically, what have I mentioned is that we have proven the concept of switchable dual function materials, but what we have not shown yet, which we are in the progress of finding out in collaboration with the University of Seville, is how does the surface structure affect these activity and selectivity patterns that we're seeing. Now, I will present some initial findings on some of the work that we're doing on plastics upcycling, which is to mention that there are various sources of plastics. We have things like from plastic bottles to all the way to what's being released into the waters directly through washing our clothes, for example. And we decided to look into this problem of micro nanofiber shedding from washing our clothes. We have some synthetic clothes that if we were to wash, they release a lot of micro and nanofibers. Now, if you ever use the dryer, you know that dryer lint is also consisting of these fibers. If you're washing only natural fibers, they have a certain biodegradation profile in water. If you're washing synthetic fibers, they can be very detrimental to aquatic life. What we know is that now, especially targeting these washing machines because they release the plastics directly into the water in huge quantities, is that we can develop filters to capture these microfibers. However, there is currently no method to dispose of them. We are simply asked to put them into the landfill. That's again putting these fibers back into the environment, which is not ideal. So what we looked at in our lab with Sylvia, who was leading this project, was to focus on some of the valorization techniques that are applicable to bulk plastics and seeing if we can develop feasible systems to upcycle nanofibers so that they are completely removed from this waste scenario. And in particular, we looked at pyrolysis, catalytic pyrolysis, and hydrothermal carbonization. We were interested to study the pyrolysis profile of polyester and cotton, which are the dominant fabrics in the industry. And we believe this can be a good way for us to target carbon nanostructures and hydrogen. Because we want to take the carbon directly out of this carbon cycle. We wanted our carbon product to be valuable, but also produce a clean fuel as byproduct. So this is the initial study that Sylvia performed, looking at the pyrolysis of polyester versus cotton. We can see that there's some challenges associated with the catalyst design in this case because we are producing a lot of different gas phase products, potentially corresponding to different solid phase products as well. And we will always end up with a mixture of polyester and cotton because people wash their clothes together. They don't separate polyester from cotton. So now the question becomes, okay, we can use thermogravimetric analysis on the solids to characterize the carbon structures we get. Ultimately, we want to make a useful carbon and hydrogen. So now the challenge lies ahead for Sylvia's PhD to design a catalyst that can achieve this selectivity. And here we strive to kind of lay the foundation for what we are dealing with in terms of this. But if we sort that out, this is potentially hugely promising because what we get as a feedstock is going to be fairly pure nanostructured materials to start with because they will be collected from washing machines. Similarly, for hydrothermal carbonization, we studied the same deconstruction of cotton and polyester. We can see the destruction of the original structure. We can characterize the carbon materials that are being formed as a result. And what we are targeting now is to look at some, especially bimetallic catalysts, which can direct the selectivity towards the products that we desire. So to kind of briefly summarize that is that we are now investigating the potential to valorize waste that would otherwise become part of the carbon cycle. Okay, finally, to conclude, I've shown you a lot of different proofs of concept. Like I said, what is needed is to accelerate materials discovery, and this can only be achieved through characterization and also being able to use computational techniques to speed up our search for new catalysts. I'll end with that, with some acknowledgements. Of course, would not be possible without the people that actually did the experiment. So thank you.
Thank you, Melis. Right, fantastic presentation, very inspiring. We have time for just one quick question to try to stick to the program. Sergio, of course.
Thank you very much for the nice presentation. Actually, I have two questions. I will have to skip one. You mentioned about cycles, absorption, release of methane. What is the time that we are talking about? What is the scale? How long it takes from the absorption to the release, for example?
Yes, so I mean, we are currently operating at laboratory scale reactors, right? So a few hundred milligrams, which means that our adsorption capacity is quite limited in the current scenario. So most of the CO2 adsorption will happen in a matter of minutes and will saturate the adsorbent. Now the peak of methanation actually, or any of these products, they form quite fast. So that peak that I'm showing you actually desorbs in a matter of, again, a few minutes. So we can run cycle after cycle. Now there's room for optimization because we haven't tried pulse experiments. So what would be really nice would be to use pulses of hydrogen or methane rather than a steady state continuous flow to try to control that desorption of products to smooth out sort of the generation of the product that we have.
Thank you, Sergio. Thank you, Melis. Thank you very much.
All right, thank you.
Right, so the last presentation before we move to lunch is from Néstor Escalona from Chile, also a partner in this project. So
yes, good time, huh?
Yeah, I think we have we're a bit tight, but that's all right. We have this problem with the Mac, so right, the floor is yours.
Okay. Hello everyone, thank you very much for the opportunity to show my research. And the title is the heterogeneous catalyst for the conversion of the biomass derived compound. Now I want to show on the short introduction related with the topic. Okay. Now this is very known to the increase of the different energy in the world. You can see to the what is the point? Okay, you can see the increase of the renewable energy in the future. It's very clear. That is very good. However, increase also to the oil, because the oil is very important. The oil is related with the petroleum. The petroleum is, at the moment, is impossible to live without petroleum, because the petroleum today is to get many things, the fuel and the chemicals. However, the use the petroleum in the combustion increase a lot of the CO2 emission. This is related with the increase the population around the world. That the other thing is true. The petroleum in the future it will run out. Okay. However, you can see in this figure the CO2, the forecast is increase the CO2 in the future. That is the huge problem because it's related with the greenhouse effect. That is very important. For this reason, it's necessary to look for different energy or different renewable energy. The solar, hydroelectric, geothermal, tyndall, or biomass. The first renewable energy is only to orientation to get electricity. However, the biomass is possible to get electricity, however, chemicals. The lignin cellulosic is constituted by 3 different groups. The cellulose, lignin, hemicellulose. This is the different range, the different compound. The hemicellulose is constituted by the pentose and hexose with the polymerization of the cellulose to get these compounds. And the lignin is a morph material constituted for this compound. And the glucose is the principal molecules from the cellulose. Okay, this is the range. It depends on the soft biomass or hard biomass, depends on the lignin. little comparison on the refinery and the biorefinery is very important to orientation of the research. Okay, it's very clear that the petroleum is the principal resource in the world at the moment. By petroleum, by distillation, it's possible to get hydrocarbon. Is the hydrocarbon by and different reaction adjustment of the molar weight to get the gasoline, diesel, and jet fuel. This is only to the cracking. However, when it is necessary to get the chemical products, the higher hydrocarbon is necessary to put a different reaction, addition of the oxygen. The other way, the biomass is the polymerization, the different process by pretreatment, hydrolysis, pyrolysis, to get the molecules platform. The molecular platform include different oxygen group. In this case, is more easy in comparison with the petroleum to get the chemicals. However, to get the gasoline, diesel, jet fuel, it is necessary to remove the oxygen by the different reaction, hydrogenation, hydrodeoxygenation, and adjust the different molar weight in case to get jet fuel is necessary alone condensation. Anyway, different reaction to get this resource from the biomass. Okay, normally when the people to speak say to comparison the refinery or the biorefinery, normally it's the opposite. Yeah, refinery or refinery. Okay, in the case, what is the different way to transformation of the biomass? The biomass is possible to transform by hydrolysis, gasification, or pyrolysis. In the case of hydrolysis, is the separation of the different components, hemicellulose, cellulose, and lignin, in order to get molecules platform. The lignin is very refractory material. The possibility to transformation is by pyrolysis. Pyrolysis is to get the BIOALL. BIOALL is similar to petroleum, however, it's very far because the different properties is very different with the petroleum. The heating values is very low, is the high content of oxygen in the BIOALL. However, the BIOALL is very attractive because it constitutes around to the 400 different molecules. Okay, this molecule is possible to get different components related with the phenolic. This is the many molecules from the biomass derived, the guaiacol, legulinic acid, furfural, phenol, succinic acid, glycerol, anisole. In our wood, this is a different molecular. At the moment, we are working in different transformation and this molecular for different catalysts. This reaction has been carried out in different catalysts in my group: rhenium, copper, nickel, for the guaiacol, furfural, glycerol, legulinic acid, succinic acid, anisole, and phenol in different animation. Different support have been studied in our group for different acid-basic properties, different metal, different anything. In the case of the guaiacol, for transformation in different compounds is very attractive for different reactions. In this case, for example, toluene from the guaiacol is big challenge. This is the application for the different industries of phenol, and the benzene, the guaiacol, this also very, very big challenge. In the case the cycloxene, adhesive, elastone, and methyl cyclohexanone. Okay, this is the introduction. Now I want to show for me is very attractive history related with the rhenium. Rhenium is the very good metal, very good catalyst for transformation of the different biomass, the different components in other added value products. Okay. Rhenium is a product of the molybdenum. Molybdenum is a product of the copper. So it's obvious. I'm from Chile. So copper is very important. Rhenium is very important for the Chilean people. We have a lot of the rhenium. However, it's very expensive. Okay. Rhenium, the first reaction, or the first paper related with the rhenium, is a different active phase for the transformation of the guaiacol and 300 degrees and the 5 megapascal of the pressure. You can see this reaction is carried out was carried out in the part reactor. You can see then the rhenium oxide, rhenium sulfide, rhenium metallic is supported in the silica. The behavior is very different, okay, and the product also. Yeah, this in comparison together with the initial rate in in this project you have the initial rate. The rhenium oxide is more active in comparison with the other catalyst. This is very attractive. This is a commercial catalyst. Okay, the question is why? Why this catalyst is active? In the initial, it's never to think is that this catalyst is active. However, it's very surprised for the result. Okay, the catalyst was characterization. This is the rhenium metallic. It's before reaction, after reaction, the increased particle size, this result indicate to the increased particle size, maybe to centralization. Now, this is very, very clear. In the other catalyst, is the rhenium oxide, before reaction, after reaction, XPS show that this value is the atomic ratio. This is increased. Now, this suggests this maybe to redispersion of the rhenium oxide after reaction. The positive behavior you can see for the sulfur rhenium sulfide, the value decrease maybe to centralization after reaction. The other thing is possible to get this figure is the rhenium oxide is only 2 species on the support. After reaction appear the other species. Normally, these values are related with the rhenium metallic. In the case of the rhenium sulfide, the species is very stable. However, in the case of the rhenium metallic, after reaction appear the oxidation species. Normally, the rhenium metallic is not stable. In the case of the rhenium oxide, is not stable as well. Okay, the question now is, why is active the rhenium oxide? Okay, and the kinetic study related with the different active site was carried out for my group. In this case, 2 different models was proposed. This model is related with the sulfur catalyst. It's 2 active sites. This metallic, this associated with the rhenium sulfide. In the other model, is similar to the only one active site, similar to the metallic active site. Okay, this is the limitation state associated with this reaction. This is the final equation. This, in this case, is the same way. This is the final equation. It's a little different. Okay, now. It's necessary to carry out different experiments to get initial rate and the correlation to comprove what is the model for the different catalysts. In the case, the rhenium sulfide, when to increase the concentration, the initial rate increase. In the other way, the rhenium oxide is the maximum, it then decrease. Okay, this is the equation for the first model. This is equation the second model. This is the linear and the linear equation. Then, in the plot, you can see this is the is the correlation with, this is the better correlation for the rhenium sulfide associated with this catalyst. However, this is not very good correlation. In the case of the rhenium oxide, this is the good correlation, suggest that this rhenium oxide is similar to the metallic. It's very, very attractive. This result suggests that the rhenium oxide in the experimental condition is create the vacancy. Okay? For the next word is the mixture and the rhenium oxide and the molybdenum oxide. This is the textural properties. This is the textural property. This is the nominal content. Normally, is all the catalysts have the same density metal in the surface, close to the 2.3. This is the textural property. The activity is very attractive. Look, this is only molybdenum oxide. This is only rhenium oxide. When to the mixture, the different ratio with the rhenium oxide, molybdenum oxide, increase the activity. Look, increase the maximum, decrease. This is the reaction, the transformation of the phenol in the patch reactor, 300 degree temperature, 5 megapascal of the pressure. To get this initial rate, you can see here. This is the initial rate. Normally, is over the dotted line is very clear to the synergy. This is very, very attractive. However, now is understand what happened with this. Okay, so normally it's no synergy. This point will be over this point, this line. Okay, the other thing, in this case of the catalyst, is only too selective. Adenosine in the other catalyst is selective the cyclohexene. This increase cyclohexene and decrease benzene. This is related with the intrinsic selectivity of different materials. Now, the objective is understand what happened with this. Okay. This is very attractive characterization for the catalyst to understand interaction in the different oxide. Look the intensity. All intensity, the designation of different species is very clear. However, the intensity is very attractive. This is only molybdenum oxide. This is only rhenium oxide. When in the mixture, the increase the rhenium, this value decrease, and decrease. This result suggests an interaction in the rhenium oxide and the molybdenum oxide. Maybe the molybdenum oxide give the density to the rhenium oxide, increase the vacancy. The XPS and APR suggest the same conclusion. The final active site related with the rhenium is the rhenium carbide. The rhenium carbide is thinking for this research is related with to increase of the stability of the rhenium in the reaction. For this reason, you can see in this plot is this is the initial rate. Okay, the star is the initial rate. This is the conversion to get the different selectivity. The comparison of the different products is the same conversion. Okay, you can see this is the different temperature of the carburization. This is a different species to get with the different characteristic techniques. Okay, at this temperature, 500 is different species on the support. Okay, in this case, active carbon is associated with the rhenium oxy carbide, the rhenium metallics, and the rhenium oxide. Okay, different species is similar for the other temperature is practically is the same active safe. When they increase the temperature at 600, decrease of the activity is only 2 active space on the support associated with the rhenium carbide and the rhenium oxide. However, when the temperature increase at these values, it's only this species on the support active. Then when the temperature increase, the temperature only active safe on the support associated with the rhenium carbide. This is the more active. This is the more active in comparison to the water catalyst. Maybe the oxygen or the vacancy or no stoichiometric catalyst or tip phase is more attractive for this reaction. The final word is the effect of the different mixture for the carburization. This is only ethylene, this is only hydrogen. Okay, this is the max balance in this case. In the previous slide, this star associated with the initial rate, in this case, is associated with the carbon balance. Okay, this is very low carbon balance. It is the last catalyst or last condition is the high values. This is the conversion as is very similar because it's possible to get the different selectivity and the same conversion. Yeah, look at in this relation, the mixture of the carburization is normally the principal product is associated with the catechol, then the phenol, and this condition increase the formation of the catechol. Okay, look at this table, the initial rate for this catalyst or this condition is very low, then and this value increase the initial rate, if this and the other is very similar, okay? However, what happened with the CO uptake is very low. This result suggests that this renio is very low dispersion. However, for this value, increase is huge, increase the CO uptake, suggests the very good dispersion. What happened in this region? Okay, different catalysts were characterization for different techniques, and it's possible to summarize the result in this figure. When the catalyst is carburization in high ethylene content and hydrogen, appear different carbon layer. The carbon layer, normal blocking of the active site, the textural property of this catalyst in this region is very low in comparison with the other experimental condition. However, when it is the low ethylene in hydrogen, is very active, is no blocking of the pores in the catalyst, its activity increase. Okay, thank you very much for sky attention, and thank you very much for the different project, put the money for carry out my research. Thank you very much.
Thank you, Nestor. Very nice talk indeed. Congratulations on your work. Right, so any questions in the room? We have time for one, actually, so we comply with the program. Any comments? Angela, please.
Nestor, you may remember that we tried to start a project on gas phase H2O of such precursors, which unfortunately was not funded. My question is, did you go further into this direction, or is this work you are doing still focused on liquid phase H2O?
Associated with the uranium?
In general, I mean, for the gas phase H2O, probably not rhenium catalysts are the best choice.
Yeah, gas phase is very challenging. Yes, maybe I think it's more applicated in the liquid phase. Because the gas phase is possible to get very good result to the characterization of the catalyst, understand what the active site. However, I think in the future maybe it's more attractive working in the liquid phase, because it's possible to scale up this reaction for the future.
So you are not working in the gas phase? You in your group, you are not working?
No, working in gas phase. No, at the moment. At the moment.
And another question, what could be a replacement for the expensable rhenium? I mean, your catalysts contain, I think, 5% of rhenium,
10%.
which is 10%.
10% for the carbide.
So it's maybe quite expensive. So is there any opportunity to replace this by
Very good
base
question.
metals, or?
Very good question. At the moment, for me, the rhenium is free. Okay. So I had a company, if they give me the rhenium, I'm very happy for this.
Yeah.
Okay.
So you are in a fortunate
for the other research, it's very expensive. For me, it's free. Okay. Now, yes, it's very expensive around the world, the rhenium. However, this is for you only. Rhenium is I think it is necessary to. It's not very stable, the rhenium in the reaction. After reaction, I don't like, because to change the phase, maybe this is the big problem for thinking for the industry. However, now in my group, I'm working to put the core shell is more stable for the reaction. This is my research. But however, rhenium is very expensive.
Okay, thank you.
Thank you for you.
All right, thank you, Nestor, very much. Sorry, I'm too wanting to comply with the agenda, but it's all right.
Fast as always.
Professor.
Nestor, I was thinking that you have got some oxide with a metallic character, you said. And I was remember my solid state chemistry lectures, and then there's all that stuff, rhenium oxide, molybdenum, rhenium, and so on, are metallic in character when you put hydrogen in the holes, and then you get bronzes.
Yes.
Have you tried bronzes for doing the same reaction without rhenium?
Maybe. Maybe because very know the bronzes is associated with the tungsten, yes?
Well,
Yes,
tungsten,
tungsten,
moly, rhenium, all that.
Yeah, maybe.
There are even bronzes using vanadium.
Okay. But I don't know what the preparation, what is the temperature to get the bronze?
I don't remember because I never tried, but I know that just from my lectures of solid state chemistry, that you can make bronzes, and then all that bronze may hold hydrogen within the structure. It's quite easy well, it's probably a possibility for
very
HDO,
good question.
for HDO.
I look at information about this. Maybe it's possible to get information. Is very well. Yes, thank you very much.
Actually, there are plenty of papers from colleagues in ITQ in Valencia dealing with bronzes. I probably you are related to those guys. Well, because he's wondering about the preparation, so you.
Yes, because
I think we can help you to find the preparation. For
okay.
bronzes. Super.
Thank you.
Thank you, Nestor. Thank you very much.
No, thank you for you.
Right, so we finish in the first scientific program in the morning, and now we're gonna go for lunch. All the invited speakers and students, you are free in the afternoon, so you guys go enjoy the city and the weather. And for BIOALL team, we have to meet up again after lunch back here to the institute. Sorry, we have to do some work. So, well, it's gonna be in this building, but in the first floor, right? Okay, I'll meet you up in the front. Right, thank you, everyone. By the way, there is a bus waiting for us, right? And so that's the point. So let us meet up, all of us in the hall, right? And we'll take you to the bus. Good. All right. Do you know what?